Hi, I'm Naz. I'm the CEO and founder of Rebel and the author of Developer Life and maintainer of the Rebel Tree Crates. I believe that open source comes from an open heart and from the joy of coding. In today's video, we're going to talk about flattening a two-dimensional array into a one-dimensional array in order to leverage memory locality and single instruction, multiple data speedups by using a real world example that I've encountered in building the Rebel TUI framework or the crate. So before jumping into the live coding section, I wanted to elaborate on the use case a little bit more to give a sense of what inspired the need to do this. So in the Rebel TUI crate, what it does is it's kind of like React, but for it's like responsive. It allows you to build responsive applications for terminals, and it leans heavily on Elm. If you're familiar with Solid.js, React, JSX, CSS, that kind of sort of vibes. So the idea is that you describe your application as a composition of components, and when you provide some input through keyboard, mouse, or application signals, they end up generating the state, mutating the state. When the state mutates, it ends up triggering a paint. So it renders, and then that render may or may not issue a paint. And the way it works under the hood, without getting too far into the details, is that the key data structure in the sort of compositing and painting pipeline is something called an off-screen buffer, which is a vec of pixel char. And a pixel char is a character like A, B, C, whatever, along with some attributes like bold, underline, strike through, a foreground color, and a background color. So some styling and the actual, let's say, text or the glyph that needs to be painted. So because it's a terminal emulator, the glyphs don't actually get painted. They don't get rasterized in a traditional GPU sense or graphics sense. What ends up happening is that ANSI escape sequences get generated, which end up getting written to standard out, and that standard out is interpreted by the terminal emulator, which then renders it like, let's say, if you have a terminal with, let's say 80 columns by 40 rows, and you say paint the pixel char at row and column 00 to the letter A, which is red, then it'll basically issue an ANSI escape sequence that provides a bunch of instructions that end up moving the cursor to position 00, painting the letter A, and applying the appropriate foreground color, like red. And all of that gets basically turned into ANSI escape sequences, which get written to the standard out. So, so to kind of take a step back beyond this interface with the terminal emulator, the way the 2D array works is that for the very first render of an application, it paints actually, let me see where the arrow goes. Oh, here, right. It paints every single pixel char on the screen because it assumes the screen is empty because it clears the screen out, and then it paints every single. So you can think of it like Helix or Vim. It's what they call an alternate mode TUI application, and so. For the first render, an off-screen buffer is populated, filled with a bunch of pixel chars representing every single pixel that needs to be painted to the terminal emulator, and that gets painted. The second render, what it does is it generates another off-screen buffer, and this time it doesn't just blindly paint it. It actually diffs it against the one that's already, it knows that it's been painted, and then it only paints the diffs, the chunks that have changed. And so this is the setup. Like I had to spend a little bit of time explaining like why you're going to see some of these things. Also, Rebel TUI has a full virtual terminal emulator environment, and that's just a fancy way of saying you can build your own tmux in the Rebel TUI crate. And so what that means is that a PTY a multiplexer is provided along with a way to parse VT100 ANSI escape sequences. So it's a bit complicated, and I don't want to get into the PTY. I'll probably do a different video on PTY later, but essentially there's this off-screen buffer data structures, and it's used not just by full-screen Rebel 2A applications like you see, like you would imagine, like building a text editor, a responsive text editor, uh, or like a Helix. Let's say it's not Helix doesn't use Rebel 2E, but you can imagine writing something like a Helix with Rebel 2E, and that's the use case I've described. And there's a different set of use cases which are derived from if you want to build teamworks using Rebel 2E. So with all that said, that's a lot of setup. Now I want to get into the live coding section and actually walk through all the different pieces that we need to put together in order to showcase, like, what does the vec of vec approach look like? What does the flattened one-dimensional array look like? And then you don't have to take my word for it. I'm going to write some benchmarks so that we can actually see what the performance differences are between the two, and not just for a made up like U size or U16 or U8 payload for the vec of T, where T is like a U size. We'll actually use a real pixel chart, the one that's from the Rebel 2E code base, so we have like a real world sense or feel for what the performance implications of going one approach versus the other are. Okay, so let's get started by creating a new crate where we're gonna use that to let's see, let's use this folder, and what we're gonna do here is we're gonna make a new crate. We're gonna say flat 2D array, and then let's see, flat 2D array, excellent. So we have let's see. Yeah, so we have an empty crate, and the first thing I'm going to do is create the sort of the scalar version of the code, which is the vec of type T, so that we actually have a baseline for what we're going to optimize in just a moment. So let us open this in VS Code. What is this? What is going on? Okay. All right, is it trusted? All right, cool. So let's see. Let's, oops, what the heck is this? Let us make, well, actually, one more thing we need to do is I'm gonna, for benchmarks, I'm gonna use cargo bench. So not like criterion or anything. So for that, we need to use the nightly toolchain. So I'm going to do that here. So, okay, we've set up the nightly toolchain, and then the first thing we need to do is, let's say we're going to make flat 2D array. So, oops, sorry, not flat 2D array. What is this? Pubmod vec 2D array. Yeah. So that'll be our first, oops, that's a vec 2D array. This is going to be our first file that we're going to create, in which we will put this struct, which is this is the sort of like a stripped down, or this is the backing storage for something like an off-screen buffer in the Rebel 2E code base, if you want to think of it that way. And actually, let me just let me see. Let me just put this up real quick so we have like so you know what the URL is. It's this one. So Rebel 2E is in the Rebel open core repo, and you can check it out here. There's all kinds of, there's readmes, examples, all kinds of things. Like, it's pretty extensive. So I just wanted to put that up there. Okay, so now let us go back to where we were. So we're going to make a struct, and this struct is going to be pretty simplistic. So it's just going to be vec of 2D array. We're going to take a type which is generic, and what is this? Oh yeah, that's right. So actually here I'm just going to say allow bytecode, just so that we can get rid of these warnings, linter warnings. So here we have our two-dimensional array, where it's a fixed size two-dimensional array where we know the ahead of time we know the size of it, and then let's see, where do we go? So that's the rows and columns, that's the size. And then what we do is when we create it, we allocate the appropriate, like the vec in memory. So we need a constructor. Then we need a couple more methods, and this is kind of setting up, like, this is to represent what an off-screen buffer needs. In general, you can think of it as a two-dimensional array capabilities that you need if you're going to make a two-dimensional array data structure. So we need to iterate, we need to diff, remember the thing with the paint diffing. We need to clear, because again, this is meant to represent a screen in a terminal emulator. So, and we need to scroll, so we need to shift items up and down. So that's kind of like the sort of the mental model going into this. Without further ado, let us create the constructors. We're going to do, so implement t vec to the array of t, and we're going to do a constructor. So we're going to say pub new empty. Actually, we're going to say, let's just do new. I guess if we do like new, we can do like a new where, we could do like a, pass like a default value that we, yeah, let's do that. Let's do new, and we're going to say rows, usize, columns, usize, and then actually, let's do this. What is this? And then, oops, and then we're going to do right. Actually, one thing I just realized, let's do this cargo add rebel tui, because I actually want to pull in two things from rebel tui, something called pixel char, and I don't like usize. So for rows we're going to use row height, and for columns we're going to use column width. There we go. These are just new types in the rebel tui crate, this thing, where essentially it's a wrapper on top of usize, but there's something called bounce checking, which is really, really nice. It eliminates off by one errors if you use these types. Rust type system is amazing, and the algebraic data types are awesome. And it took me a couple of years to figure out how to use it effectively. But yeah, these are one of the really cool things. Like, instead of using usize everywhere, you can use, like row height, and like for such a simple example, it doesn't really make that much difference, but I just wanted to use it anyway. Okay, so now first thing we need to do is we need to create, what the heck? We need to create a, let's see, we need to create a data where, this is pretty straightforward, right? We need, essentially, again, this is a bit of a made up use of rows and columns. I mean, I'm just basically converting it to a usize. So rows, we're going to say, oh, we just say rows, and columns, we just pass those through. Okay, so here we have our constructor. And so now what we want to do is add a default. So the default is going to be of type T. And what I want to do is, instead of just creating a vec with capacity, I also want to initialize it with a default. So let's see. How do you do that? I'm sure there's a method for this. Where the heck is it? New. Oh, with capacity? No, that's just with capacity. How do I initialize it with the default? Initialize? No? Oh, apparently that's not a thing. All right, so let's see if I can find out from here. Let's see, in Rust, can I create a new vec with a default value? Let's see. You absolutely can. Oh, no, that's not it. Resize. What? vec new resize. What? Initialized an empty string. Vec default. But what? Oh, I see, I see. So we can do vec defaulters. Oops. Okay, that makes sense. Okay, so now we need to have some trait bounds. So let's put this. So in rest, the trait bounds have to go everywhere. So if I put them here, I'd have to replicate them on all the impl blocks. So I'm just gonna put it here. Let's add a trait bound for. Okay, there we go. Done. So now we have our. Oops. We need to turn this into as use size. This is admittedly not the best use case or demonstration of why to use a new type for this, but there's other situations where this comes in handy, especially when you want to compare index type values to width or height type values, because one is 0 based, the other is 1 based, and that's where this kind of stuff shines. Okay, so so there's our new. Let's actually add some unit tests along the way. Let's do this. Mod tests. Oops, tests. Yes, and use super, and we're gonna do test. Let's say fn test new or test constructor. This is refreshing, typing code by hand without actually using an LLM to generate all of it. So it's kind of fun. All right. So, oh, what is it complaining about? Oh, you know what? I'm just gonna say allow dead code and unused imports, so we don't get unused imports. What's wrong with this thing? Wow. Is Clippy unused imports? What is wrong? No. Unused imports? That took a long time. Okay. Oh, right. And it won't affect this because it's a test code. So we can just put it here in the test module. There we go. All right, cool. Okay, so we're gonna test our constructor. So that's good enough. Make a new constructor and make sure they're all the default value. Let's see if that works. Great, wonderful. All right, so with that done, wow, that's taking a long time to compile. Still going. All right, there we go. It worked. Great. Okay, so our constructor is done. Yay. So the other things we want to do beyond construction is we want a method to clear the screen, so to speak. And again, this is a 2D array of pixel char, or T in this case, but clear is like you clear the data structure and you paint it and end up like clearing the terminal screen, if you want to think of it that way. So let's see. 1 second. Okay, so let's implement the clear method here. So this is, I guess, very similar to what we did with, actually not default. This is going to be, well, what do we clear with? I think I'm going to clear with. So let's see, with it, it, whatever. So what this is going to do is just take the vec and wait and fill it, not by cloning value, but oops. I was like, wow, that's easy. We don't need to vectorize anything. That is not the correct data structure now, is it? So yeah. Oops. So here we need to do something a little bit different. So here we're going to have, let's see, in the constructor, we need to fill. So for each one of these, what happens if we do this? Let's say data So we have a vec which contains, what the heck is this? Vec which contains, that's a line. And then this is however many lines. So let's see if we can make this a little bit easier to read. Now what does it want? Oh, this is not right. So we need to do this. Let us see. So here, let's do this. Let's say let line equals, and take out this vec. So because it's this, what this, it's not easy to read. So let's just do this. We're gonna do, the line is that, and we can then create like lines, which is like that, and then the data is going to be like the lines. You don't think of it this way. And then so we have the vec of, so the vec of the columns, that's one line, and then for replicate that for the number of rows that are provided here. So, and then the test should pass here. I don't think we even didn't know. No implementation. What? Oh, oopsie. Ah, so T must not only be cloned, but it has to be partially Q, I think. Get that sorted out. No. What is it saying? Yeah, partially Q. Let's see. Does that not solve it? That's weird. I think there was just like a delay in the Rust analyzer updating, whatever. Okay, anyway. So I think, let's see, cargo test, does that work? Nope. Let's see, no implementation, cannot compare vec of integer with integer. Well, oops, haha, so that's not the issue. My bad, because this is not right. We have to iterate the rows and columns, so, oops, wow. Okay, so here we need to do a for loop. So we can say for, oh my goodness. So let's just take out this partially Q. I mean, it's not bad to have it here, but that's not what the problem was. Okay, so let's do a cargo test. Does that work? What's the issue here? Is my test completely nonsense now that I have, what is, vec, oh, right. It's not, oh my goodness, I have to redo this. Let's do these assertions again. So we want assert eq, what assertions do we want? We want, actually, this pretty much does the whole thing. I don't think we need any more than that. Yeah, there we go. Because we're literally iterating through every single row and column, and we are in a scalar way. That means one at a time. We're not doing any vector or SIMD stuff here. This is purely scalar. All right, let's do the clear. Again, same kind of thing. We're just gonna iterate through every single row and column, like one at a time. And this is not fast. This is actually, oops, what's the issue here? This is not fast. This is actually quite slow because if you visualize, let me see, I have a diagram for this. Let's visualize this here. Why is this slow? So, oops, the heck. I don't want to draw this by hand, so I actually had it drawn before. So here, the way the vec of vecs is organized is that the first vec has pointers to all the other vecs. So each row, if you will, or each line. So here we called it lines. Where is it? We could have called it row. And here we could have called it rows. So, whoops, sure. Yes? No? I don't think I did. What was that? Rows? Oh, oops. That's what it was saying. I see. So we can say vec of rows. How's that? All right. So the vec of rows, if the first array is the vec of rows, and what that does is it contains pointers to each of the other rows. So if you look at memory layout, the vec of vec, which is data, has an array, and that array doesn't actually contain pixel charts or type, cells of type T. It just contains pointers. So if I want to access any item in row 1 using data, I have to basically dereference the data, the vec, to get to this first array. Then I have to find the first item or the first row, dereference it, and then jump to a different location in memory to get the any item of that first row or row 1, and that takes about 300 CPU cycles. So that each jump is because that row 1 hasn't been loaded into memory yet. So there's something called prefetching, where there's the CPU, when you go to access, let's say the data, the first vec, it'll end up using the cache line, which I think on Intel CPUs is about 64 bytes, I think. Let's see, there's a command for this. What is it called? Get conf. Yes, 64 bytes. So the 64 bytes at a time, the CPU will, anytime you access memory, it won't just load 1 byte, it'll load 64 bytes, and then it won't just give it to you directly. It'll actually put it in L1 cache. So the L1 cache then ends up getting populated with the first time we access like data. So for example, when we do self.data, right there, it ends up, causing the CPU to load this chunk of memory into the L1 cache. And then once it's in the L1 cache, the CPU can then go do stuff with that data. And when it goes to do stuff with that data, where was it? So we say self.data, and then we give it a row. So let's say it's a row 1. Doesn't matter. It's not in this array. So it has to go to a different location in the heap, in system memory, in the virtual address space of your process, which gets mapped to a physical memory location in your RAM. That then will get loaded into the cache line, and that will then populate the L1 cache. And then if we keep accessing items in row 1, which we do here for each column, then we're okay, because it's loaded all the columns in row 1. Oh, not all, 64 bytes of the columns in row 1. And since let's say if T is less than 64 bytes, let's say it's 1 byte, so you can end up loading 64 items in that row 1 array at a time, so per CPU cycle. And there's something called I think a hardware prefetcher, which even while CPU instructions are executing, this thing actually goes and tries to predict what the next RAM access will be. So then it continuously tries to pre-fill the L1 cache, so that when the CPU instructions get around to it like this, it won't have to waste time doing the row and column loading into memory and stuff. So because it's a vec of vec, we're essentially fighting with the hardware, because the hardware is just like not happy with how we've organized this. Like, we get some memory locality in a given row, in row 1, but as soon as we jump, like let's say we go to the end of row 1 and we go to the start of row 2, now we got to do another pointer jump. So we got to go back, get this from here, we got to go to that, then we got to load this. So that's a lot of jumping back and forth, and it doesn't look like much. Like this code, you're like, wow, why is this should be really fast, and not really, because of the memory locality. It's like there's no defeating physics, and that is precisely why in the benchmarks we're going to see the slowness of this compared to the speediness of the 1D version. And so this is just kind of like like I'm kind of like elaborating on certain concepts as we run into them. And so So I'll introduce this notion of SIMD as soon as we get to it. But this is kind of like cache locality, or you want to call memory locality in action. Okay, so I haven't written any benchmarks yet, so you just have to take my word for it that this is not fast. But we will demonstrate this. You don't have to take my word for it. We will write benchmarks so that we'll see like how much faster the SIMD equivalent of this is compared to the scalar version. So the scalar, or the SIMD, or the vectorized version versus the scalar version. Okay. So with that said, that's just the clear method. All right. So we have a few more methods we want to implement before we can actually do I test for this? No. Let me just have the yeah, test clear. Sure. Just write the test. Seriously. Huh? Why is this not writing the whole test in one go? What's happening? The heck is this? Huh. Okay. Why don't you just do this assertion? I don't understand. Okay, so row 2, 3, okay, default value is 0. Well, that's not clear it's 0. Let's do 100. And new value. What? Oh, what? We don't need default value. What's going? Oh, okay, new value. Oops, my bad. New value. Yes, default value of 0 is fine. So the default value is 0, the new value is 5. So after we clear it, everything should be the new value. Okay, this should work. Excellent. All right. So let's make sure all our tests pass. We're good. Oh, by the way, this is a cool cool thing. You can run all kinds of, I'm in Arch Linux, but you can run all kinds of cool commands like this to get the L2 cache size, the default stack size for a process, all kinds of stuff. Linux is awesome. All right. So let's see, where are we so far? So we have the new function or method done, we got the clear method done, and we got a few more methods, and then let's see. Okay, let's implement the scroll up method now. There's just a few more left, and then we can jump to the flattening, the flat data structure. So let's see. This one is scroll up, and what this will do is it will simply shift all the items in the vec of x, basically all the rows, up by 1, and the last row it'll just copy the second last row. So if I were to put a ASCII diagram, I prepared this ahead of time, so I wouldn't have to type this. So it kind of, yeah. So basically, you start with you shift all the, because we have a vec of x, so each line is a separate vec. So we can like shift up the whole thing by 1 and then just clone the very last item. So this is actually pretty straightforward. This one is so if the cell data is empty, then we do nothing. And then otherwise we can do let's see, we can do cell data, I think it's rotate, is it left? Yeah, rotate left by 1. So this is this actually doesn't move anything, because this is actually where we're taking advantage of the fact that we have a vec of x. And this is actually a benefit of having a vec of x, which there's the downsides, but this is actually not a downside. This is a benefit where we don't actually have to move any of the memory, because it can be where it's at. We just swap the pointers, basically shift all the pointers by 1, but we do just have to clone the very last row. So, but this is blazingly quick. Like, this is not a slow thing with the vec of vec. This is actually a benefit of using vec of vec, this particular use case. So there's always pros and cons. There's no you know, nothing is for free, and nothing is yeah, nothing is without trade-offs. So we can do something like this. If the let's get the length of this thing. So self.data.length. So if the length, why is it putting -1? So the length is greater than 1, then what we can do is that's pretty much it. So we take the second last row, and then let's see. Yeah, this is, oops, this is really copy of second last row, and we then simply assign it to the last row. So this is the last row. So last row equals, gets a copy of the second last row. And I think that pretty much, yeah, this is one of them unintuitive things where it's like not everything is bad. This is actually better. We'll see when we do the scroll up implementation with the contiguous or the flat one-dimensional array. The vec of vec is actually faster than that, like by a large margin. Okay, so we need, let's see, a test scroll up. Let's see, what does it do? Makes a new thingy, okay, populates it. Why is it using I32? What? Why? Ah, I see. Let's see, so it is, all right, let's see what it's doing. So it makes a new data structure, fills the array with distinct values for testing. Okay, so it just puts, I see, different values in there, and it scrolls up, and then it goes vec of 2 and 3. Oh, I see. It put like random values in there. Oh, it's just a 3x2 grid. Oh, wow. All right, that's fine. Yeah, it's just checking that the exactly. All right, that works. We don't need to scrutinize this further. All right, excellent. So that is the scroll up method that's done, and then we have actually two more methods. Let me do those. Or actually, let me do one thing real quick. Yeah, and then let's see. The next one is going to be actually we can do this is a bit of a made up one where for telemetry in the Rebel TUI, I display the memory size of different of the data structures. So there's actually a speed benefit of flattening it, and so I will show the downside of implementing the get memory size for a vec of vec, because let's see. So we do get memory size because we have to, if you look at that diagram, the pointer one, to get the size of it, we have to like traverse a bunch of stuff. Actually, we can make assumptions. We never traverse it, but actually no, we don't have to traverse it because it depends. If we assume that each row is the same width, which it is, then I don't think we need to traverse it. Let's see. This might be more straightforward than I thought. So let's see this. So if we have get memory size, we're going to say, so we got total size is memory size of self, but this actually is just a container. It doesn't actually have the data. So then we have to go get the data. So then we can say total, because that's just the struct, the vec of x, this thing. That's the size, but we need to go get the size of each one of these and then add it all up. So here we can say the total equals the self data capacity plus the, oh, sorry, the capacity multiplied by, so the capacity, I see. So this is the number of rows, if you will. And now we need to find out what the size of each row is. So we can say size of a row. Then we can say size of a row is actually the we can do it this way, or we can say let's see, size of a row is the size of the vec of t, and then the total would be, let's say, okay, so the total we have is the size of cell, which is this structure. So what this is, then we have the size of a row is the vec of t, and then I don't think this is right. So I think I'm doing this wrong. Let's try this again. I think what I am. So we have the number of rows. Actually, let's see. So this gives us, this is the struct itself. Then this is the, sorry, that was a struct itself, and this is the um so if that's the struct, this is the, let's see, size of a row. So this is the capacity. The capacity, this is number of rows multiplied by the size of a row. So this gives us the data. Then I wonder if we need to get the for each row, do we need to find the, so this is the vec of t multiplied by the number of rows. Okay, and then we need, and then this one is the vec of t, I think, for each row. Yeah, so so we need to do for row in exactly. Okay, that makes sense. So it's actually 3 steps. One is the struct itself, then is the this thing, the vec of whatever, and then this essentially this the size of this. So if I were to, the size of this, and then the size of vec of t for each row. Okay, that makes sense. So this is for, I hope that makes sense. Like there's there's a struct that holds this stuff, but then the data, this is just a, that the size of this is not the actual allocated uh, uh, the actually allocated size of in memory. So we have to kind of dereference it twice in order to get the struct size, the first vec size, and then because there's the number of rows, so we can think of this as like the number of rows is that, because that's the it's a vec containing a vec of t, so the capacity is the number of rows. So here we can just say number of rows, number of rows, and then that gives us the size of the first vec, and then inside of the first vec we have a bunch of other vecs, and this is containing the columns. And so that's why we are getting the columns, or if you want to think of it as cells. Wow. So that's more about the memory layout, or how the, not the memory layout, how the struct is actually organized in order to get the size. So there we go. And then now let's see, do we have a test for the size? I wonder what the what we would even do for the size. Let's see if we can write a test for the size. Let's see what the this thing will do. Yeah, test get memory size. All right. So wonder why it's not doing the whole thing at once. Okay. So we make a new vec2d array of 2 by 3 with some default value. Ugh, always puts I32. Should do usize, and then this way, I think that's usize. Oh boy, is that right? Expected size is vec2d array. Okay, iter blah blah blah. This is basically just typing out what we just did. All right, that works. All right, perfect. So yeah, that makes sense. Okay, so we have the, actually, let me make a commit real quick. So here we have the get memory size handled. And then the very last method, this one is actually that the diffing function, where if I have one off-screen buffer or one vec2d array, and I provide another vec2d array, like this gives me the essentially the a vec of rows and columns that are different between the two. And so this is something we're going to speed up radically with the SIMD version. So that's why I'm providing the scalar version here. So this is, we're going to do a diff of self and other, self and other, where we will return a vec of, let's see, of we are going to get a vec of row and column. So that's row height and column. Wait, did I mess this up? Row height, column width. I think. Uh-oh. Oh no. This was supposed to be column index, not column width. My bad. So let's just do search and replace column index. Wow. So many mistakes in today's video. Actually, let's do this index. And let's do a to do here. All right. So let's see, column index. All right, so here, so the code is going to go something like this. We need to hold the changes, right? So mute, let's see, let mute changes. This is what we're going to return. And then we are going to have, it's okay, it will know this in a minute. Actually, it'll be a vec of row height and column index. Okay, and then that's what we're going to return. And then the logic is going to be something like, is that right? Binary operation cannot be applied. Oh, okay. So we need partial EQ. Okay, so here's the input block. What is this? So let's do another input block for this. So we can just here we do plus partial EQ. Okay. So what this does is that it essentially iterates through both of these arrays. This is a very slow iteration, and essentially for each row, for each column in both of these things, it's like it's comparing one by one, and then it's very slow. So this is something we can radically improve with the flattened version. So this is an extremely slow implementation. This is like admittedly kind of not that great. Okay, so here if we were to make a test of this, let's do that real quick, and then that will wrap up the let's see, that will wrap up the wait, what? Okay, so we have an array 1. Why does this need to be mutable then? Oh, I see. Okay, so it made 2 arrays, and then why didn't it just clone the other one? No? Ah, because we didn't say this is clone. There we go. That should do the trick. Yeah, so we just clone it, modify some stuff in array 2, and then we look for changes, and let's see. So it changed, what was the default? Default is 0, and it changed some items to 1 and 2. Okay, and then it's saying that 0 and 1 and 1 and 0. Okay, oh wow. Okay, let's see if this works. Not a bad test, actually. Hey, that works. Okay, so we have just implemented the diff. Let's see. So with that, that actually wraps the implementations for Vectorization array. I just noticed something silly that I did. Oh my goodness, being the silly goose that I am, I I still haven't gotten these types right. So okay, let's fix this once and for all. So the rows are supposed to be row height, and the columns are not supposed to be column index. They are supposed to be column width, and that should sort it. I think everything else should just work. Yeah, and to solidify this, so I don't mess it up anymore, I'm going to do something even more type safe. This was completely unintentional. I wasn't intending to show this, but yeah, that's just me making a mistake. Okay, there we go. That works. So here you can see like we have you know, something like rows and columns with the default. So what we can do here is we can make a different constructor. So we can say something like new 2, and this will take a arg. So this is a size, or arg size. This is impl, let's say into size, and then it can take a default of type T. And what this can do is we got to import size row, and then let's see. Oh, let's do this. Where's the imports? Yeah, that's just import size. And this should be row height, column width. That's correct. And let's also import row and height. So width and height. And here we can say rows, row height, columns is column width. And here, the first thing we can do is this. We can say let size is arg size into. So this allows us to do the following. And then we can actually call new, which I'm gonna, we can just do essentially copy this and put it here. So here, the thinking is that we can pass in, actually, let me fix this real quick. So this is arg size, which is size dot column width, and then here we can do let's see, rows. So we have size dot row height. Okay, that should get rid of the errors. And it cannot find rows because we need now rows is a row height, which we can get from size. So we can say size dot row height, and here we can say size dot column width. So this allows us to write code like this actually. So we can say we can say something. Actually, why am I writing this in a dot test? We can just write it in a test. So we can do, let's see, new to. So if I make a test and I say fn test new to, we should be able to just do like, so we can say let width equals, let's say 10, and let height is 10, why not? And then, so we have a width and a height. And then now we can say let grid equals vec2d array new, and then here I can say width plus height, and the default can be, let's say 0, something like that. So this one, oops, my bad, this is new 2. And then there we go. So essentially what this means is whatever. So we can say so here what this means is that it just in the implementation of these new types for row height and column width, I actually have I overloaded the plus operator, so that when you plus add a sign or add, I think, a width and height, you get a size. So I think this is easier to read and more ergonomic. So now that we've done this, we know this works. So we can just rename, like get rid of the old one because I don't want to be confused by this, and just replace it with a new one. And let's just rename. We're going to dump this into the test suite below. And no more confusion with stuff. And then there's some mechanical refactoring I have to do because remember it was taking the rows and columns. So I just have to replace that with like that. So, and if I can, since there's, it's just like the same thing over and over again, I can just say rows plus columns, and that should sort it. There we go. And here we can just say allow and use imports as the very top. I think if we do this, it applies to everything in the file, so as opposed to just this statement. So I think that should have done this to begin with. So there you go. I think, let me make sure I didn't screw anything up. So yeah, it's a little bit different, where I just wanted to fix that once and for all because that was just, and in fact, we don't even need rows and columns. We could have just made this a size. I mean, let's see how many accessors we have for this. So yeah, it's fine. I'll leave it as is. It's just like, it's just a little convenience that you can you can pass it whatever it is that can be turned into a size. And in our case, that is like, if you look at the usages, like width and height, height and width, essentially. So the add operator. So hopefully this makes more sense. And let's see, rows. If I don't know if these field names make sense. Maybe I should just call this row height and column width, or height and width, perhaps. You know what? I'll just leave it. So yeah, I don't want to get too far into refactoring this for better readability, but yeah, there you go. I just wanted to replace that, and then now that this is finished, we can actually look at the flat implementation. And yeah, so let's do that next. So before actually starting the flat 1D implementation of this 2D array, I wanted to cover the performance implications real quick. So um, the as we kind of covered, just kind of summarize briefly, like because we have a vec of vex, that ends up messing up our cache locale, or that's not really that memory is not contiguous. It's in different places in the physical RAM, and so the hardware prefetcher has a difficult time. I mean, it can't essentially prefetch and put all this stuff in the L1 cache in advance of this memory being needed for various operations, like all these methods that we have. And that's just a consequence of essentially having a vec of x. So inside of the row, memory is contiguous, but outside of it, it is not. So yeah, and then what we're going to do next is we're going to use an array. We're going to take the vec of x and we're going to model it as an array. But one of the the benefit of that will be that because it's memory will be contiguous, the hardware prefetcher will be able to do its job for many operations, as we will see, and that the number of cycles wasted will go way down. So like let's say you access your, let's say the access pattern is you're trying to get everything in a row, or you're getting multiple rows. Within that one row, your cache locality is good, but as soon as you jump from one row to the next one, the cache locality is not good, because you're now jumping to a pointer in a different location for the subsequent row. And just to kind of put a number on it, it's 300 clock cycles, roughly. CPU cycles is the delay. And I wanted to put some numbers so we can see this. Here's my, yeah, here we go. So I have for the Rebel, the Rebel 2E crate. This is just a Rust docs for it, and so you can use getconf level 1 dcache line size, this command, to get the like it's 64 bytes on my x86 machine. I have an Intel CPU, but yeah, this is a nice, neat little command to see what your cache line size is. And then oh, these are broken. I need to fix these. Then let's see. So this is a hardware prefetcher. You can actually go to this. I'll put a link to this actually in the description of the video. But yeah, so the penalties, this is what I was trying to show, is that if something is prefetched and you have a cache hit in the L1 cache, it's really good. You can the CPU can fetch the data and load it into a register within 1 to 4 clock cycles, and once it's in the register, it can do whatever operations it needs on it. L2 is okay. As you can see, L1 cache is pretty small, it's 32K. L2 cache is bigger, but slower, but still not too bad. L3 cache, 33 megs, slightly larger. Yeah, okay, 10 times more clock cycles. But check this out. Main RAM fetch is pretty awful. It's like, 300 clock cycles. So that can slow things down significantly when we're getting to hundreds of times slower. So and then the the SIMD and the vectorization work we're about to do with the 1D array, what we're gonna take advantage of the fact that the Intel modern x86 CPUs have these instructions, single instruction, multiple data, where basically the bottom line is that as long as the data is contiguous in memory, there are certain operations that the CPU can do very quickly because it leverages the hardware prefetcher, and instead of like fetching like one chunk of memory and doing some operation on it, it prefetches a whole chunk of them, and then by issuing a single instruction on all of those chunks of memory, it can in a very short amount of time get that done within like just a clock cycle or two or three. And it doesn't really matter how big those chunks are, because it can prefetch them. As you saw, there's 3 layers of caches, so it's very smart about, like, even if these chunks are huge, it won't like choke out the CPU or anything. So it's pretty amazing. Like, so we're gonna see all of this in action in just a moment, and there's some rules of thumb which will actually cover all of this in the live coding portion. But yeah, I just wanted to give a sense of like what the numbers are, and what hardware stuff is happening. And I also have a tutorial on developer life I just posted. All this information is in here as well, so you can see actually, let's see, CPU cache, yeah. So you can see like let's see, you can see like all of this there as well. So I'll end up uh, putting links to this in the video description, so you don't have to remember any of this. But yeah, so with that said, now we're finally ready to go into the 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 vectorization of this data structure. So let's start with creating the file for the flat array, basically. So we can call it 2D flat array. So it's not it's 10H files. So let's create this, and here the biggest difference, I mean, we've kind of gone through most of it, but the biggest change is going to be that the array, or the grid of type T, is now going to be, instead of a vec of x, we're just going to use a one-dimensional array. So in order to do that, let's see. Let me throw some diagrams up there anyway. So we saw this earlier in the other file, the vec2d array, but this one, this is basically what we're going to be focusing on now. So this is the oops. So this one should be like that. So this is the previous one, and this is the current one. Actually, we should probably, oh, there you go, something like that. So instead of the scattered heap memory, this one is going to do the contiguous memory. So so unlike the let's see, unlike the other one, let's see, let's do this. We're going to do obstruct. This one's going to be flat. Let's see, 2D array of type T. I think that's going to be clonable. And then we're going to do the data is the thing that's going to be different here. So we're going to do an array of type T, which is boxed. So it's going to be on the heap, not the stack. That's what this is. And the way we're going to actually instantiate this is going to be, we're going to make a new vec, and then we're just going to drop I think it's capacity field. So essentially a vec that we won't be able to mutate. So when I do the constructor, I'll show that. So I think same as before, rows are going to be row height, and the columns are going to be column height. So that's great. Now, before I get into the implementation, one thing I just wanted to point out real quick is that going from a two-dimensional array to a one-dimensional array, we're going to have to do some arithmetic to do indexing to get to a particular cell. So, so for example, I actually have a diagram for this. So one thing we want to do is we want to go from a this is I don't know why I made these Rust mod level docs. They should just be Rust docs. There we go. So one of the things, one second, let me copy the diagrams correctly. So let's see, I have one more diagram I want to get. Okay, so let's see, this is actually, this is what we were doing. This is what we're doing now. So let me just maybe, here we go. Okay, so the if you think about the array access pattern, we have like in order to get something, we just do the angle brackets, right? So angle brackets is given the row index, and then the angle brackets given the column index. Given that we're switching from a 2D to a 1D array, like we have to now translate the rows and columns into the one-dimensional array index inside of our backing store, or our data. So let's see, if you think about it, let's see, here we have like because we don't have a row and a column anymore. It's no longer a vec of x. So we just have like one really long vec where the contents of row 1 are placed at the start. Right at the end of that, the contents of row 2 followed by the contents of row 3. So given that if we're given a row and a column, a position, essentially to index a row column and a row index and a column index, which is the position inside of the grid, we have to translate that into our one-dimensional array. And essentially the math goes something like, we take the in order to get to the final index, we take we have to get the row. So it kind of goes like this. We get the row offset for the this thing, whatever it is the value of the row indexes, and we do that by multiplying the row with the given row index with the width. So it kind of goes like this. So the row offset is the given the row index multiplied by the width, and so you can think of it this way. And then the final index, or the index of the actual item in the 1D index, if you will. This is actually the row offset plus column index. So that's how we arrive at, that's the math essentially. So in order to get to the one-dimensional index, we take the row index multiplied by the width and add the column index. And if you look at this, so if the example is get the cell at row 1 column 2, which is, this is the grid, then when we flatten this out into a one-dimensional array, we end up getting the let's say for row 1, we do 1 multiplied by the width, which actually puts us here, because remember now this is flattened. And then actually this diagram is pretty misleading. I should probably redo this with like showing it end to end rather than, because this makes it look like it's a grid and it's not. It's actually more like it's more like, how would I do this? It's essentially this, like repeated let's see, kind of like that, where if we do something like this, it's going to be index 2, then this is going to be index 3, it's going to be index 4, it's going to be index 5, and so on. So, and then eventually it will lead to, let's say, if we do this, so this will be index 5, 6, 7, and 8. There we go. And then this one, let's see, these actually, there we go, something like that. And so they're no longer in, this kind of goes away because that didn't make any sense. And then we just need these symbols here. So there we go. And then something like that. So, and then I think we can do, yeah. So here actually, let me just finish up this, oops, box. And here we need a, there we go. All right. So now this makes sense. So basically if I want, so if you want to think of it this way, this is like column 0, so we can do it this way. So for, this is row 0, like, and this is the linear index, so to speak, right? Like, oops, let me do this. Yeah, this is a much better diagram. So here we have row 0, and then we can do something like, oops, and here we have row 1, and then we can do this, and oops, what the heck, and then there we go. Okay, that makes sense. So that diagram was not very good. I'm gonna have to review that diagram in other places too. And then actually the other diagram makes sense when we think about going from, actually, we can try this. So this is the equivalent if you want to think of it this way. So we have the, so here is the, oops, yeah, so this is the 2-dimensional grid that we had before. And since we flattened it into the 1-dimensional grid, then this is that translation. So we end up going from one to the other. So let's see. Yeah. So there you go. So that's how, so, you know, given a row and a column, we just take the row index, multiply it by the width, and that gives us the correct row offset. Then we add the column, and then we can jump right to the appropriate column. So that allows us to translate from this 2D address space. This is our 2D grid, and this is our 1D grid. 1D grid equivalent. Yeah, that diagram was not very good. So there you go. This is a much better diagram. And so this is the, because in order to do indexing into this, into the 2-dimensional array, even though it's backed by a 1-dimensional array, we just need to do this, this math, and we'll get that. So that's the address translation from a 2-dimensional coordinate space to a 1-dimensional coordinate space. Unsurprisingly, we have to do the opposite as well, which is, if for example, so this was the 2D to 1D mapping is like when we want to do array access given the row and the column index. The inverse, we need to do that when given a particular location in that 1-dimensional array. If we want to find what the row and column is, because let's say we want to, in the case of a terminal user interface, we want to update the specific row and column and the screen, then we need to translate the internal 1-dimensional array into a row and a column position. And so to do that, we have to flip the math, so to speak. And so the way that looks like is that we, given that this is the underlying data structure, so this is the, let's see, this is the one-dimensional grid. And so we're going from the one-dimensional grid to the two-dimensional coordinate space. So 2D, 2D grid equivalent. So if we pick a particular, let's say, index position 5, which is this one, so we can say if this is the what is it greater than? So this is index, yeah, index to position 5, let's say. So we start at this, what is the row in the column for this? So we can look it up here. We can say, oh, this is row 1, column 2, because there's our translation, because we can read it from the diagram. But mathematically, the way we do this is that starting with the 1D index, which is 5 in this case, we have to get the row index, and we do that by index divided by width. So it's basically the flip of the previous one where we got the row offset by doing a row index multiplied by width. So we just basically reverse the operation. And then in order to get because we added the column index, the only kind of interesting thing here is we have to use the modulus operator, and that gives us the difference. So essentially, we're just flipping this this equation on its head in order to get the 1D to the 2D. And there's some implications actually of doing this math that we'll get into later, but I don't want to like give that away. But but this is kind of like a good starting point. Let's see. Yeah, because later on when we vectorize this, I mean, this is vectorized, but when we start leveraging SIMD instructions instead of doing this sort of thinking about it from a like a scalar API perspective, when we think about the vectorized API, we'll do equivalent functions, but we will do them differently. And all that is a bit vague at this point, but I have examples for everything coming up in just a minute. Okay, so now that we have the struct, we need we basically need to build out the equivalent of the equivalent API that we had for the scalar version. Now we have to basically build the vector version. So let's see, I was just updating the diagrams because actually my diagrams were wrong. I'm actually publishing this to GitHub as well as a tutorial, so I just want to make sure I have the correct diagrams available. Okay, so let's do this. So now we need an impl block for similar kind of things we did here. So we had a constructor, so let's make a constructor. So we're going to say impl flat 2D array of t, and I think let's see, we're going to do we'll deal with the trade bounds later. So t, what, clone, okay. Okay, and then because we have that here. Okay, so we can add more here, but at the very least we can't go less than what we've defined for the struct. So in this simple block, we're going to have a constructor, and the constructor is going to take an argument size, which is going to be the impl into size, similar to what we saw before, and the default value is a t. And we need to import size. Okay. And then here, what else do we need? I think that's good. And then let's make a test module. So let's say mod tests. That's good. Let's see. Oh, we need to import width and height. Let me just grab all the imports from here. Okay, great. And so for our new function, Okay, sure, that's fine. So what we're going to do is, actually, this is correct. So we get the size by turning arg size, we call into to get the size. Then to get the total number of cells or items in this one-dimensional array, we just multiply by the row and the column. And then we create a vec of that, which is correct. And what is the problem here? Oh, shoot. I forgot to return self. There we go. So check this out. Vec of cells, which is the one-dimensional array. So I guess we could just call it 1D vec 1D. And then in order to turn the vec 1D into a boxed uh, array of T, we just do into boxed slice, and it converts a vector into a box slice. So exactly, it discards the excess capacity, and it doesn't allow it to be resized because it's an array. So it's not it's a very quick operation. This is not like yeah, converts the vec. Before doing the conversion, it trims excess capacity. So very straightforward. Okay, so that gives us our boxed array of type T. And then I think I don't know what we need to do in the constructor. I guess just check that uh, assert that. What is this? Why is this not working? What? Hello? Assert. I'm sorry, what? So it created a grid of 100 items. So we need to do 4. Yeah, there you go. Assert that it's 0. That should be all that we need. So let's see. Yep, that works. Excellent. I guess we can also do this. We can say assert eq grid is vec of 0 u size 100 items, right? Because that's essentially the same thing. And why is it complaining now? Partial eq. Oh, okay. So let's do that. Partial eq. And then we got to do that here too. Partial eq. Is that the problem? Let's see what the cargo check says. Grid of vec. The trait debug is not implemented. Oh, did not know that. Let's do debug. And then add a debug here. What is the problem? So we import the debug trait. Okay. That was a strange error message. Let's see if that fixes it. Nope. Does not implement debug, but it does. Flat 2D array U size does not implement. Oh, shoot! I did the wrong thing. It was complaining that the struct is not the ugh. Okay, let's do this. Derive debug and clone. Not that the T has to have debug or partial EQ. So we don't need these. That was just unnecessary. Okay, does that work? No, it does need partial EQ. Really? Oh. Partial EQ must, oh, the struct is missing partial EQ. Okay, I'm like missing the, let me collapse this is too much. So here we need partial, because I'm comparing the, and now what's the problem? Ah, right. So this needs, like, I'm comparing a vec to, so I need to do into box slice, and that should work. Found struct, oh geez, data. There we go. Wow, that was a lot of work for this one-liner. But this should work. Nope, it doesn't work. What's the problem? The left is 0, 0, 0, and the right is 0, 100. What? Is that not what we did? Literally, vec of default value. That's weird. 1, 1, 1. I think I had it backwards. There's default. No, no, I did not have it backwards. This does not make any sense. Let's see. So the default value, that's the syntax, is the default value, and then okay. So default num cells. So we got 1D vec. We put that 1D vec into the data field. So now if I say grid.data, okay, let's do this. Let grid equals grid.data. What do we got here? It's a box of usize. So this is grid, and let's just say other equals this, and then because I'm like trying to break down why is this not working. So that's vec of usize. Okay, so we can say let other equals other into box slice, and now that's box of usize. So what's the issue? This is the same type. Box of usize. This is box of usize. And so if I say, so let's do this. Before we just do grid and other, we can do grid.length is the same. Let's see if that works. No, 2. Oh, what the heck? How is this 2? Grid.length. Wait, let's clear this. Okay, so it says the left is 100, so this is 100, and this is 2. What? The default value, I think that's a default value, and then the size. So we have 100 items. I don't get it. How on earth is this? That doesn't make any sense. What am I not getting here? Other into box slice is 2. What if I don't do box slice? Let's see. Still 2. How the heck is this 2? Let's do this. No, not grid. Other. Okay, let's see what the heck it's. Other is 0, 100. What about grid? So that's, the grid is correct, 0, 0, 0, 0, and the other is 0, 100. I thought we created the exact same way. Vec default num cells, where the num cells is, this is 100. And then I did vec 1D into box slice. And then here we have flat 2D array, which is this thing. Width and height, which this will give us a size. So if we say let size equal width plus height, you can see the size is S, so this will be, and then we can assert okay, and then So we can see here, print line, the sizes should be 100. Yeah, size is 10 width, 10 height. Yeah, 10 by 10, which is, that's 100. So what? And then grid.data. So we got grid here, other here. And then let's see if that works. Nope. I am totally not understanding. Why is this 2? Other is 2. What? So we do vec with capacity 100. And then we can say other.fill 0 usize. Is that not the same? Now let's see if it's any different. What? Left is 100, right is 0. This is bizarro land. That's a box of usize. This is a box of usize. And what? It's saying the grid is 100 zeros and other is blank. That is weird. What if I don't turn into a box usize? Same thing. Back with capacity. So if we made a vec.new, how big is it? Length is 0. This is so with capacity. Constructors new empty vec with the specified capacity, but there are no allocations. Oh no. Wait, what? So I have to okay, so let's do this. So we can say new with capacity 100. That makes me, but that doesn't mean it's allocated. So I have to insert 100 items in it. So can I say fill 1? Okay. But I have to now extend it because now I have to say other.extend from within. Extend, no, set. How do I resize it? Extend from within. What? What is happening here? Resize? Is there resize? Okay. Resize with. Resize the vec in place so that the length is now equal to new length. Okay. The new length is 100. And what is this? New length and f. Oh, that's the. So that just gives us usize. It's a function that produces the default value. I guess I could have just done resize, not with. I could have done this. I could have just said resize and then drop that function. What? Oh, we can just do this. Then I don't need the fill. Okay, let's see if this works. Oh my goodness. So what the heck? That was weird. Don't know why vec didn't work. So this basically manually creates a vec of capacity 100, then it sizes it to 100, basically allocates it, and then allocates it zeros. So why couldn't I just replace this with let other equals vec, like should that not just work? What the heck did I do wrong? Did I do 100 U size? Oh no. Oops. Oh boy. Okay. This is not a good macro syntax. Yeah. Okay. So I don't know what the first item is, and I don't know what the second item is. This is not good. Vec allows to be defined as SIMD. Yes, yes. Okay, so 1:3. So that's a default value, and that's the size, I'm assuming. Oops. So this is the value, the default value, you can say. And this is the size. Okay. Oops. So here we have, that's exactly what I thought, default value and size. Okay, honestly, I have no idea what happened, but that was a very strange rabbit hole to go down. Anyway, so it's working. So this is 100, not 2, obviously. And so yeah, there you go. Overly complicated test debugging. So there we go. It works. Excellent. So here we have this proves that under the hood, the grid, which is in this the flat 2D arrays data, is just a one-dimensional array which you can create with just a vec, like this statement. Oops, like that. So there's the default value and there's the size. So that works. Excellent. All right, let's see, and let us commit this real quick. All right. So excellent, new constructor is done. So that took a long time to build the new constructor. So here we have similar other functions. Clear, I'm going to take a reference to self, mutable reference to self, and I want, that's the type that we will basically replace it with, clear the every single item with, and here I can like simply like the simplest thing to do here, because it is a one-dimensional array, I can just fill it. Like, I guess if I wanted to do it like one cell at a time, I could do it the other way, doing the integer math, which I will show. This isn't made up. Like I don't think this is the, like, oops, what the heck is this? So here we can say, let columns equals like self, get the number of columns, and then we can get like, get the number of rows, and then we can do for each row, for row in 0 rows, and then for column in columns, we get the row offset. This is the, actually, why is it doing clone? Because I think, oh, T is clone. Let's make it copy. All right. Okay, cool. Okay, so here, does everything work? Cargo test. Okay, so here, I just iterate through every single row, and then for each row, I get the, for each column, I get the index by doing that math. The rows multiplied by the columns, which is width, and then yeah, and then just set each one. This is naive. We're going to replace this with the SIMD equivalent, because there is no reason to do this 2D to 1D address transformation, because under the hood, this thing is just a 1D array. So when we do the SIMD version of this, you'll see this implementation gets much simpler. But just to provide the scalar equivalent, kind of I'm doing it this way. All right, let's do the mem size. Get mem size u size. So this one is going to be much simpler because we just have like the total is the size of the struct, and then we have because it's a one-dimensional array, we just add like the type of t multiplied by the length of the array. That's essentially. So this is super duper easy. This one got like super easy. So here we can write a test for test clear. Oops. Yes, clear. Yep. Actually, I don't know what the heck it's doing. Let's just do this. Okay, so we make a new thing, a new grid. We clear it with one U size, and then we should just be able to write now. So the other will be one U size, and we should be able to do an assertion like that, where we, oh wait, you know what? There we just did grid length, but we could have just done grid and other. I guess I could keep the length. I don't know why I'm dropping that. So here we can just do grid and other. This will work. This is what I was aiming to do in the first place, but it became, somehow I read the vec macro wrong. Okay, so here, let's see, we could just do this. And this one, you know, because it's into box slice. There we go. Oh, right, and it's grid dot data. So let's see, that should work. Yep, that works. No big deal. And then we can get the size. Let's do a fn test size. Wait, get memory size. Same thing. We got like 100 items. Then we make a flat 2D array containing just 0. We get the memory size. Wait, what? There's no assertion. And the assertion is what the is memory size should be the size of the struct itself. Yep, that's right. This is correct. So let's do this, and it works. Yay. Okay, excellent. So far, so good. So clear is working, and get memory size is working. Let me commit this. All right. So what else we got? We have, I think we had a scroll up. Yeah, we had a scroll, a diff, and a print. Did we have a print screen in the other one? Oh, no, we didn't. Why didn't we add a print screen to that one? It doesn't matter. Actually, let's see. I think we just need, actually, let's do this. Next one I'm going to do is print screen, because I wanted to show the 1D to 2D address space conversion. So this is kind of just a made up function that does that. Print screen. So what this does is it takes, actually, let's just return a string. Okay, so, and what we're going to do here is that we're going to make a, oh wait, buffer, and we're going to return the buffer. And so here, what we're going to do is that, let's see, let's get the number of columns equals that. Then we're going to say for index item so we're going to essentially enumerate that one-dimensional array. So I don't know what the heck all this is. So here we do okay, so we got the one-dimensional array that we're enumerating, and then let's do this. So the row index inside is going to be index divided by columns. In other words, this is the width. I don't know if we can call it width. Columns is fine. And then we can say let column equals index and then divided by columns. So that's the modulus operator. Sorry, not divided by, modulo columns. And that'll give us, that's the math that was done here. So the 1D to equivalent 2D grid mapping with the division and the modulus operator. We need both in this case. And then, so now we have the row and the column index, because we've taken this, the 1D index, so to speak, right? So, and turn it into a 2D index. And then here we can say buffer.push string, whatever, we got the row, column, and item with the character return line feed. That's fine. And then let's see. What the heck? What is this? Oh, geez. All right. Item does not implement debug. Let's make it implement debug. So this is so we can make that function work. All right, does that make the compiler happy? Yes. And then now we need to make a test for this. So we just did like print screen, right? So this is going to print out one line at a time, row column, with carriage return line feed, like what the it's translating the 1D index into a 2D index. So here we can say test print screen, and then okay, so this is nice, a smaller example of 3x3 grid where we initialize everything to a bunch of zeros, and let's see, what is it doing? Okay, and actually just so for our benefit, let's do this. Let us print. I don't think we'll see this because this test will pass. Okay, it passed. But if we wanted to see what the output looks like, it looks like that screen output, and it's like 0 0. I don't like this \n. That just looks weird. Let's see, just ditch the \n. And then let's remove these. Okay, so it'll say 0 0. You know what? That looks weird too. Maybe we can put this. Let's see. Is that easier to read? Maybe. Let's do this then. Okay, that I think that'll be a little bit more readable. So when we go to our print screen, we can just add like this at the end. And then now when we cargo test, it should be fine. And then when you run this test individually, we can, there you go. So 0 0, the 0 0 item at 0 0 0, item at 0 1 is 0. Basically it's all 0, but you can see it's going through the rows and columns. And there's 3 rows and 3 columns, so that works. Excellent. And then I think okay, so that's we're done with print screens. Let me just make a commit, and then we have 2 more: scroll up and diff. I think that we did here. Yes, let's do diff first. So where's the diff? So we're gonna do the diff function pub fn diff, where we take self and other immutable references for both, and we're going to return a vec of row and index positions, column index, that are different. Yeah. So I think this is what we're going to do. So diff, yeah, and then let's see. I think we had done something very similar here. Yeah, vec of row and row height and column width. Oh no. Oops, this is not correct. This is row index. Oops, what is this? Let's see how many instances of this there are. I think, oh boy, row height. Thought I fixed this. Row height, row index, and wait a minute. Or did I get it backwards? See, this is why I have. Let's just revert that. Let me see what we did with diff on that one. Row height. No. This should be row index and that should be column index. Oh boy. Am I using oops. It's just an isolated, it's just this method that I think needs fixing. So we can say row index. And here we can say column index. All right. Oops. Yep, row index. Actually, there's easier ways to do this. I don't know why. Oops, we got row and column. So here we can just, where's the diff? So now I'm fixing the vec2d, the vec implementation that I had messed up, unfortunately. So here we can do, instead of this complicated row index new, we can just say row, and here we can say column. And then that'll work. Oops, they're both called row. That's wonderful. Then we can just do like this, row.into and column.into. There's no reason to wrap them in those functions. Okay, so let me get rid of these. We don't need this. I think I did added the row and column. Okay, so if we look at the diff implementation, that is working. So cargo test, no? What is the problem? Oh, right. So this is not correct. This should be, let's say 0.into, and this will be 1.into, because I changed the types. Oops. Wow, I made quite a mess with that one. Let's see, 1.into. Such is life. This happens. What can you do? Oops, can do 0.into. Excellent. So at least we got that fixed. Okay, so now that that diff is fixed, we can fix the, oh, we didn't make a diff yet. Okay, so we just have print screen. All right, so in the diff function, we're going to take a reference to self and a reference to another. And then we're going to return a vec of row index and column index. And then that's going to be the signature. Then we import row and column index. Okay, great. So, oops, what is this thing doing? Okay, so here we have, why is it still wrapping? It's very strange. Oh. I think it's because, never mind. I have this extension that shows the error inline, and I think that's why it's wrapping all the way to the right. Even though there's nothing, it's just a hint. This does stuff. All right, so okay, so the diff of self and other, and we're just going to return a grid of, sorry, a vec of tuples, the row and the column index. So here, There's a thing called position that I could return instead, which is, but I don't think I did that in the other div. You know what? I didn't. So actually, let me see if I should fix this div. Oops. So there's such a thing called position. So we could do position here, and just, I don't need to, I don't know why I specified the vec type there in the first place. And then here, instead of returning a tuple, let's keep it simple and just return a row plus a column, which gives us a position. Oh, that's why, is that why I needed, no, a row? Oh, it doesn't know what row. Wait, was that? Oh, it still doesn't know. Ah, this is why there's I think it's, well, this is not that. We can do row dot into, and we can say let column is column into. And here we can specify this is and this is a column index. I didn't realize this was not going to be that. I thought I could just say row plus column into, but this doesn't really help that much. Anyway, so, and this generated a bunch of errors. So here we have row plus column, and that should do the trick. And I just have to import these. And let's say this is row of 1, column of 0, and hopefully that sorts it. No, I don't think it's a tuple anymore. Oh, we do need a reference, and that is a plus, not a comma. Okay, what other errors we got? Oops, my goodness, there we go. Or I could have just done this. I don't know why. Well, it doesn't matter. All right. Actually, I couldn't have changes. There's a vec contains. Oh, okay. No, this is correct. I think the errors are gone. It's just, yeah. Okay, great. Let's just make sure everything works. Oops. That's just a warning. Okay, great. Okay, finally. So we did modify div so it returns a position rather than a row index and a column index. So here we're gonna have changes, which is the new vec. And then let's see if it got any of this right. You know what? Let's just do this one line at a time. So let's just do the number of columns is that, the number of rows is that. So because I'm just copying the scalar algorithm basically. So and then do like that. Actually, no, it's not position. It's simply row plus column. And that's not going to work because row index is, and column index is, okay. So it looks at the index and it goes, if it's other. Oh, and I think the problem is it's not comparable. Yes, partially Q is missing. That is correct. So we need to go update this. The type has to be comparable. Otherwise, how can we do a diff? Then we can say partially cubes. then, yeah. So here we're just converting the, let's see, we're iterating through, this is a bit made up because we're like, there's a much simpler way to do this. This is just kind of like doing this artificially almost at this point, doing this translation of, well, are we doing a 1D to 2D here or 2D to 1D? Let's see. Here we are doing a, so we got the row iterator, we're going through all the rows, then for each row we're going through all the columns, we're coming up with the index based on that math, and then we're just, okay. So here we're just like converting a 2D, this is a 2D to 1D mapping, just so that we match the code that we did with the Scalar version. But we'll see in just a few moments that this is not needed at all, because we have a the vectorized version of the backing store is just a one-dimensional array. So this is where SIMD is going to be like completely just game changing. It's kind of set up for so we can compare the scalar version of something to the SIMD version of something for benchmarks. That's why. So we have apples to apples comparisons, so to speak, sort of. And then actually not sort of. It will be like the scalar version of something compared to the SIMD version of something comparison. So that's why. Okay, so we got diff done. I guess we need to write a test for this now. So fn test diff, and let's see if it'll do the whole chunk at once. Oh, I think this is the same as this diff, the test for here. So yeah, looks like it. Only we don't need, well, I don't know. This should just be row and that should just be column, because we have these useful little functions. Okay, what is it doing? It makes a grid of 2 by 2, initializes it to 0, then makes an array. Why? Just clone it. That's strange. And then modifies the array 2. Okay. And then gets the changes. There should be 2 changes, and those are the, wait, array data. Oh, okay, it's being unnecessarily. Okay, change the, I see. These are the 1D, I see. So this is the 1D to 2D mapping, basically, is what it's doing here. I mean, not really. It's more like this is 1D and this is 2D. There we go. Okay. Something like that. That's 1D and this is 2D. So this one, I guess we should do, wonder. All right, there we go. So that's one-dimensional 1D index, and this is the 2D index corresponding to that. So row 0, column 1, and row 1, column 0. Let's see if this works. Yay. All right, so we got diff working. That's fantastic. I think the last one we have to do is scroll up. Because we had a scroll up, I think, here. Although we did not have a print screen in the other one, so, because I guess the thing is backed by row and column, so they're kind of pointless. So Actually, here we can say 2D to 1D mapping. I like these little comments here. Let's see. Okay. What else? Oh, so we have scroll up. So pubfn scroll up. This one's going to mute self because it will change self. Then this one, let's see, what is it doing? So it gets the columns and the rows. It shifts all the rows up by one row, column and columns. Oh, duplicate the last row. Let's see. Okay. See if this makes any sense. Shift all the rows up by one. So row, okay, and rows by one, column, source index, destination index. So it's copying. Oh, okay. It's just copying. Wait, how does it know? So for each row, it gets all the columns and then, so this is shifting. No, this is move. Okay, what's the source index? Source index is the row plus one. Oh, okay. I see. It's shifting them up by one. All right. That's actually correct comment. Nope. Yes. This is, nope. That is not 2D to 1D mapping. This is the, exactly. The row will be replaced by the contents of row plus one. So there's some math to do that. And this duplicate the last row from the second to last row. I see. All right, fair enough. That seems right actually. This other one was way simpler. This is just I think we just had this is duplicate the last, yeah. I don't know what this is. Yeah, that's all that was. Right. This actually, that's all we did here. So yeah, this is so much simpler than all that, but I think they are doing the same thing. So let's verify that. So test scroll up and let's see. So we have a grid of 2 by 3. They're all initialized to 0. Then it fills the array with distinct values for testing. Excellent. And then, okay, so row 0 to h, h. And this is columns. Oops. Rows and columns. Okay, so for row and 0 to rows as you size, column, so one row at a time, then for each column in that row, it gets the one-dimensional index. So this is 2D to 1D mapping. And then, okay, then it fills it with distinct values. That is the same arrays. Okay. Fill with distinct values. Okay, so the value that it fills it with is the row multiplied by the columns plus column. All right, so it fills it with some number. Then it does a scroll up and it goes array data 0, row 1 becomes row 0, row 1 becomes row 0, row 2 becomes row 1. I see. Okay. That actually is a pretty awful way of visualizing this. Like if we had made a getter which had the row and the index, then that would have been much easier to read. But we can do that. We can implement index and index mute for type usize on this struct, by the way, if we wanted to give like a 2D access. So like, but let's see, we can actually, right now there is no way to do a 2D access on this one, right? Because it's a single, so we should do that. So here, I can do that here. Let me go collapse the, okay, so this is what I was talking about. I can do impl index, um, why is this being so weird? So import index for, sorry, impl index for flat 2D array usize. What the heck? Okay, index hmm. Missing generics. Trade defined here with one. Yeah, that's what I thought. That it's putting the wrong thing in the wrong place, I think. It's supposed to be yes. So it's actually usize here and T there. I don't know what the heck it's doing. And I think we had a bunch of trade constraints in there, but that's okay. Oh, we gotta do copy, copy partially Q, all those copy partially Q and debug. Perfect. So this is essentially oops, that's not right. No, that's not it, because I want the, let me think about this actually. If I want to give the syntax, actually, you know what? Let's roll this back. I think it was just, yeah, just that. Let me think on this a little bit more about how to implement that in the meantime. But I think so far what we have here is I think a complete implementation of flat 2D array. So this is good. This is good. And then we can get into comparing the two and then making benchmarks. So we needed to get to this point just to be able to make the SIMD versions of these scalar methods on the flat 2D array. That's going to be next. And then after that is benchmarks. And that's, yeah, and then we're almost there. And then then the video is finished. Actually, I think before we do that, I do want to implement that index index traits because I think it's a good idea to do that. I actually the code that I just deleted was actually correct. I don't know why I did that. So the idea is that we want to unlock so we can, if you want to look at this test, this is something like array access syntax. So what we want to do is we want to create let's see what's a, say we want to create one of these, and we want to be able to write code like this. So grid of, let's say 0 0, we want to do something like this. We can say assert is 0, and we want to say assert equals row 0 plus column 0, because that's a position. We also want that, like that's essentially the oops, The heck? We just want row and column, I think. And these won't work because this doesn't exist. That's correct, and that is also correct. Okay. So then I think we need to row and column. We don't need width. Okay. So this is the syntax that we want to unlock. And so in service of that, we can, with this in mind, so it's like grid 0, 0. These are U sizes. So what we want is, so grid 0 will return a slice, and then the second 0 will index into that slice. So we can say something like impl index. Oops, we're going to import index. So I think we do, let's see, impl index and index mute for both. What is this doing? Index. So we want index of U size for flat 2D array of T. That's 1. And then we want T over here. And then this is going to be copy partial EQ. And then let's fill out this, something like that. Okay. So this, like if we had written grid 0, right? Like that's what this is. It's just giving us a slice or grid 0. And then we can say impl, actually, let's do this. So that returned a slice. Wait, hold on, let me see. So let us comment this out and make sure this works. So I don't know why I put a comma here, but this is what I had meant to write. So cannot index into a value of type usize. Let's see. So we can, because there it is. That's how we index into a value. What? Cannot index into a value of type usize, but that's literally what this is. Index of usize. That doesn't make any sense. Let's see. Yeah, because usize indexing will return a slice of type T. So what the heck? Can I just write that? Usize. What? Uh-oh. Oh no. That was the problem. Okay. So this is not correct. This is complete. Oops, my bad. So we have to make a range. So what we want to do here is that when that auto-completed stuff was terrible. So here we want this. So basically, yeah. So essentially, when we return, so given the index, and that index is a row index, so maybe this will help if we write it out. So what I want to do is find the slice, like given a row index, what is the like what are the one-dimensional indices that I can provide in a range So I can say let range start equals columns. So let's find the columns. Okay, so that's our column, like a width basically. So the row will be, the start of the row index will be the given row index, multiplied by columns, and the range end will be range start plus columns. So then we can say, self data, and then this is going to return a slice. So let's see. And let's see. So we got a new one, and then this returns an array, usize, and that's weird. I don't know why that was so difficult to write. All right, there we go. So here we have a row slice. So we can say row slice. Then for the row slice, I can find that the column, right? So this is like let column, not column slice, like the item is, we can say something like row slice of 0. So that gives us the 0th item in the row slice, which is the item at column 0. So here we can now say the cell is 0, and we can also say assert EQ grid 0, 0 is cell. So this is index by usize, and this will be index by position. So that was almost let's see, that works. So let's do cargo test. All right, excellent. And then so that works, which is excellent. So now that was just index. So I want to do index mute as well, so we can do assignment, because it's kind of fleshing it out. So here we can do something like, the heck. So here we can do impl index mute. And for index mute, the function is different. It's actually fn index mute. Same kind of math. We need to get the range, and then we could actually extract this into a helper function, since this code is the same here. But yeah, this is the index mute. So now we can do something like we can do this is index mute by usize. So now we can do mute grid like that, which is awesome. Like now it's starting to look like, I can use array access syntax with usize, which is what we're used to. So now I've like made the ergonomics of this flat 2-dimensional array similar to that of a 1-dimensional array, which is awesome. So this is nice for API ergonomics, and then once we do the SIMD optimizations, like we can have our cake and eat it too, in a sense. Like we won't be able to use the array access index like we did just here, because SIMD, like it operates on a different, it doesn't, you don't do row index anymore. But this is still good. Like this is still I like it because it makes it more ergonomic. And then to kind of round it out, what we can do is a similar kind of thing here, where we do so you can think of this. So this is mod impl index usize, and so we can do, so this is What is this? Wildcard imports? Something like that. Let's put this up here as well. So clip the wildcard imports. So, okay. So now, oops, where the heck were we? Okay, so that was the implementation of the index and index mute given usize. So now we can do something similar. We can say mod impl index position. And so hopefully this will work. Nope. So here we're just indexing by position. And the only difference is that when we index by position, the let's see, it almost got it right. Almost. I think that's it. Yeah. So this one, it's basically just copying this code over again, the same range thing. So let's see. No, it didn't. It copied it completely wrong. Oops. Ay, caramba. Let's do this again. Come on. Autocomplete. Okay. Okay, now it's using the range. That's right. And then this one is wrong again. This is supposed to be index mute. What is this doing? Okay, so given a position, let me see. Same index. Why is this doing index mute? Why is it using? Wait, what? Why isn't it using the range syntax like over here? That's weird. I don't understand what this is doing. Yeah, the row and the column, and then columns, and then this should just be range start, and it should be range end, and that should be range start, range end. I don't know why it re-implemented, like it didn't copy the code up there. That's very strange. And neither did this. Okay. All right. Okay, I have no idea why it, who knows? Anyway, so let's see. Now, if we do index by position, cannot compare, what? What's the problem now? Grid. Why not? So that's, what? Index by position. Let's make a new grid. I don't know what the heck this is doing. All right, so let's do this. If this is indexed by usize, let's insulate these things from each other. And then let's do this. What the heck? And then we have, okay, so we have a mutable grid. Actually, we don't need mutable grid, we just need grid. Then we want to do a position, and we want to do, let's do the row slice like we did before. So we can do row slice, and then we can do cell. Then we can do assert cell as 0 or something like that. And this one, what is its problem? Okay, there we go. That's what I was anticipating it should do. And then we can do index mute by position, same thing, only now we will have a mutable grid. And okay, let's see if this works. All right. Anyway, I just wanted to add that because it's a nice thing to have the index by use size or by position implemented for this code. Then and then we'll get into SIMD next. So let me just put this in the right place. And oops, let's just throw this at the bottom. Okay, great. That is done. All right. Let's take a look at the print screen method actually, because this is going to be our segue to leap into the world of SIMD and vectorized operations. So, because we've implemented now the scalar operations for the flat two-dimensional array, and I'm going to introduce vectorization and SIMD with two use cases, so that you can wrap your head around it, because otherwise it can be a pretty vague concept. So by attaching it to use cases and access patterns, whether it's reading or writing, and whether you need like a 2D index to be derived as you're iterating through the 1D slice, or maybe you want bulk operations, these can all end up in slightly different sort of approaches that you take. So let's look at print screen. And I said, I think earlier, that the division and the modulus operator here can cause some problems. So in this example, even though if you look at what we're doing, we're just essentially taking the one-dimensional slice, right? And we're just iterating through it from beginning to end. You might think, well, this is quite fast because that's just a a boxed array of type T. It's essentially a slice in the heap. So that is true. This actually is very parallel, except that there is one downside. Given how quick these operations are because of the hardware prefetcher we talked about and using the L1, L2, and L3 caches, believe it or not, this ends up becoming a bottleneck where unless columns is perfectly divisible by 2, the division and modulus operator are really slow. So from a CPU performance perspective, like the number of clock cycles it takes to do division or modulus is quite high compared to like addition or multiplication. So even though this is integer math, it's still very slow, relatively speaking, because we've reduced there's something called Amdahl's law. And so this is kind of an expression of that. So we've sped this up, but now that this is sped up, what was acceptable before now is becoming a wall, because this is slow relative to that. And so there are actually cases where the compiler can outsmart this, but that only happens if the width of the columns, the number of columns, is perfectly divisible by 2. And for this particular use case, that's highly unlikely, because the off-screen buffer again models the size of a terminal screen, and unless you exactly size it, by modulus of sorry, by orders by a number that divides perfectly by 2, not perfectly by 2. It's like for example, actually, let me just show you the code. This is easier than to talk about it and just show it. So here's the actually, where do I put this? This is an impl block. So let us do this. Let us drop a bookmark here. Okay, so we're gonna come back to this, and we don't need to scroll up. Okay, so I'm just gonna drop it here for no good reason. So let's add a test. So let's say that this is slow division. And then here we can do something like this, where let's say the columns, the use size is exactly divisible by 2, so 128, which is 2 to the power 7, right? Then let's see. Then what we can do, um, perfect power of 2. Sorry, not divisible by 2. Not even or odd, but power of 2. So 2 to the power n equals that number. So then let's say, so this is the made up example where this will work. So the other cases for which this will work is 2 to the power 6, 2 to the power 5, 2 to the power, and so on. Like, but those are, pretty big jumps. Like that's not like one, unless you resize your terminal screen so that it is perfectly a number, the width is a number of columns is exactly a perfect power of 2, like this is not going to work. So in most cases this is not going to work. This is just made up, but I'm just showing that this is the only weird sort of edge case where the compiler can optimize this particular division modulus operator using something called bit shifting. I'm just showing this because even though it's made up, it's like this will kind of further sort of more reasons to vectorize. Let's put it that way. So here, I can do calls log what is it? I log. This is where you go basically the opposite. So this is how you get like 7 from what is this? Oh, it's a spelling. iLog. Do I have C spell? Oh, yeah. We can just do this. Actually, you know what? I'm making this more complicated. Let's go to the bookmark. Show bookmark. I think there's an easier way to do that. But anyway, actually, how do you traverse bookmarks? I think it's like control. There's a way to jump to a bookmark. Control Alt L. Huh? Oh, jump to next. Hit show. Show bookmarks. Nope, that's that. Okay, whatever. Anyway, oops. Where are we? I think it's like show bookmarks. Bookmarks view. No, in file. Let's see. Jump to next. Jump to list from all files. Control Shift K. Hey, this is what I was looking for. There we go. Control Shift K. All right, that makes it more useful. Okay, so let's look at slow division and throw a bookmark here too. So toggle. All right. Okay, so iLog. Let us do this. So okay, so there's our function that takes the width of the number of columns, and it'll give you the power of 2 that comes out of it. So you can see here, returns the base 2 logarithm of the number rounded down. Oops. Yeah, whatever. Sure, whatever. Okay, so so this is again a made-up example where this will work because 128 is perfectly divisible. Sorry, I keep saying divisible. It's perfect power of 2. So then we can do const mask amount. This is to demonstrate bit shift optimization essentially. So this is 127. So okay, and then now let's say we're looking for an index which is I don't know, use size of 5, like 5, and we're going to convert it to like a row and column, right? So here we can do something like row. This is the 1D to 2D transformation. So we can say 1D, yeah, whatever. So actually not using, but using bitwise operations instead. Exactly. So actually let's just do this not using. All right, and then so the row, here's the thing, it's going to be index shifted by the shift amount, and this is a replacement for index divided by columns. And then we can do column is index and then bitwise and. So this is going to be division is replaced with bit shift, and modulo is replaced with bitwise and operations. So these are the so this is the hack. So it's not a hack. It's like this is under the hood. LLVM will be doing this if it sees that, oh, okay, whatever the number of columns is in this case is a perfect power of 2, which highly unlikely. And then finally we can just print it, whatever, something like that. So there you go. This is the sort of the slow division. This is not slow division. This is like corner case, slow division, corner case speed up using bitwise, bit shift, bit up, bit whatever was it, bit operations. It's bit mask, bitwise. Operations is, yeah. So this is super duper edge KC. Let me throw that in the. This is. I don't know if there's really a test. Let's just throw it at like mod corner cases. And then here we can just throw that there. All right. And we don't need any imports because, this is just whatever. Some corner case thing we added. All right. So that is the sort of the optimization that is a corner case optimization, which, like I said, unless it's exactly 128 or whatever the other numbers are, it's not going to happen. So like 64, 32, 16, 8, it's highly unlikely. Okay, so that gives us the opening to now jump into SIMD and really taking advantage of the L1 cache, L2 cache, L3 cache. So the first function we're going to be looking at is, and this was why it was a segue, is print screen. Like that's going to be, what is wrong with this though? That's weird. What the heck? Blue. Let me just do this. This teaches me for using oh, Code Insiders. Wow, that's unexpected. Huh, that is very strange. Looks like VS Code crapped out. That's weird. Okay. Okay, that was weird. I don't know. What? Did it just upgrade? I have no idea what's going on. Anyway, moving on. So let's do another work in progress. All right, great. Okay, VS Code is happy. Wonderful. So the first thing we're gonna do is we're gonna address this slow division and modulus operation, because this is using a that is a vector access of the data, and this is the slowness. So this is low, and so here we're gonna speed it up. And how do we speed it up? So here's the thing. So there's 2 rules of thumb, and I'm gonna walk you through both of them. So the first rule, and I'll give you examples for each one. So this setup was just to make sure that I can demonstrate rule 1. So rule 1 is that if you do care about in this case we do 2-dimensional coordinates. So basically you want to get the 2D address space from the 1D address space as you're doing operations which are sped up by the L1 cache, which it is in this case. So you want to do a fast version of this. So how do you do a fast version of this? So your friend in this case, or our friend in this case, is something called chunks exact. So instead of using division and modulus, we're going to eliminate division and modulus operations entirely by leveraging this thing called chunks exact. And this chunks exact thing is just a slightly different way to think, but it's pretty awesome. And so this is the rule of thumb where, in this case, if you do want 2D coordinates, you do chunk exact, right? The second rule of thumb is that for certain operations where you're just doing bulk operations on huge chunks or the entire chunk or the entire slice, you don't really need to deal with indices at all. You don't care. So for example, if you want to clear out the buffer, you don't need to iterate through every single one. You can just wipe the whole buffer in one go. And that's SIMD, single instruction multiple data. In diffs, we're diffing one one-dimensional array with another one-dimensional array, right? Which the flat 2D array, the backing store is a boxed array of type T. So when we're diffing these two things, what we can do, which we will see in a moment, is with SIMD, we can actually use iterator zipping and really like speed up that thing like a lot. So so yeah, for bulk operations and for actually, let's see, that's the second one. So yeah, even for scrolling, we're gonna leverage SIMD, and it's not gonna be as fast as the Vec of Vex for scrolling. I'll say that right now, because there we just shuffled a few pointers, and that happens in nanoseconds, whereas even the SIMD optimized shifting or scrolling of the buffers is going to be like hundreds of nanoseconds, if not like maybe thousands or tens of. We'll see it actually in the benchmarks, but yeah, there's going to be a speed differential there. But so there's some is good, some is bad. So okay, with this, let's this is our first SIMD operation that we're going to implement on this struct, and I'm going to call that SIMD print screen. Very cleverly named. Let's see. And this is going to take it's exact same signature as the other one, but we're going to do let mute buffer string new, same thing. We're going to return buffer at the end. But in the middle, what we're going to do is that let's do calls equals whatever. That's the number of columns, right? So we're going to do, and here we're going to use the chunks exact. So we're going to do self.data, that's the thing, dot chunks exact. And you can look at chunks exact, which is returns an iterator over chunk size elements of the slice at a time, starting at the beginning of the slice. So it basically chunks up your slice into however many chunks, where each chunk is the chunk size. Then it says the chunk sizes, the chunks are slices and do not overlap if chunk size does not divide by the length of the slice. Then the last up to chunk size -1 elements will be omitted and can be retrieved from the remainder function of the iterator. Okay. Due to each chunk having exactly chunk size, the compiler can optimize the resulting code better. Okay, that's cool. All right, wonderful. So we're going to do the chunk size in our case is column. So if you want, we can rename this to chunk size, which is just columns, right? So this is just columns. So we're taking the columns, and that's our chunk size, and we now need to wrap this in a for loop, because that's an iterator. That's gonna return an iterator. So we're going to do enumerate because we need the index. This, by the way, is how we're going to get the position. And all of this is happening using addition. So there's no division, there's no modulus. It's just addition. So which CPUs are ridiculously fast at. So we have our row index that we're going to get. Then we have our row chunk, right, from this iterator that we just created. So maybe we can do let chunk iterator if this is easier to read. So we can do chunk iterator, and then here we can say chunk iterator enumerate, right? Yeah, this is more readable. So now we're basically getting the one of the coordinates in the 2D coordinate space right away because of this enumerate. And then what we're going to do, now that we in this loop, or in this block, now that we have the row chunk, right, chunked the buffer, or the 1D array into these sizes, then we can do something like this. We can say for column index, actually, let's just do this. So we're gonna iterate now the row iterator. So here we can say rows iterator, and here we can say columns iterator, which is going to be the row chunk, and we're going to get an iterator out of it, and we're going to enumerate it. So why don't we just get rid of this and put this here? Okay, so here we're going to do for column index, column index item in columns iterator, and then we're going to do buffer push, and that's essentially it. So there you go. This is the sort of equivalent of the code you see above it, but notice, where did the division and the modulus operator go? There aren't any, so this replaces it completely, and this is fast. So yeah, so we got the chunk size, which is the columns, right? The column width, whatever you want to call it, columns width, and then number of columns, and then actually maybe chunk size. Maybe we can say like column width. I don't know, columns, whatever. So chunks. I don't know. Naming is hard. Chunk size. Regardless, we're just chunking the 1D array, and then for each of those chunks, we end up doing this. And let's see. Let's go see if this works. And they should be equivalent. So we should be able to do a print screen and a SIMD print screen, and then we should be able to say like, okay, compare the result. You know, they should produce the same output. So let's go do a test for that. So I'm gonna put this at the bottom of the test block. So I'm going to say, what do we call this? FN test SIMD print screen. That's right. So, okay, what is this? Made a width, a height. Okay, 3 by 3. Made a grid, filled it with zeros, and now it's calling SIMD print screen. Okay, this is fine. This is like we can run this to say, all right, this is what that function, you know, should do. Let's see if it test passes, and then we're going to compare to the other one. So we're going to do a comparison test. There are going to be two parts to this test. I don't know what happened. Like VS Code, must have updated itself or something. I don't know. Anyway, so that passed because it's the same exact as the other one. If you look at the test print screen, the reason it just copied that code verbatim. So, all right, now we're going to do this. So we're going to say, this is, and then we're going to do another one. We're going to say, actually, let's do this. So this is, we got the screen output, expected output. So now for that same grid, I'm going to do let expected output scalar, and then I'm going to say print screen, right? Not SIMD print screen. So here we're going to do screen output. Actually, what is expected output? Vectorized or SIMD, whatever you want to use. And then, so let's do this. That's the grid. This is the SIMD one, and this is the scalar one. All right. So the script, oops, what is this? Expected vectorized output should be the same as the expected. So this is the SIMD version, and this is the scalar version. I know I'm using the word SIMD and vectorized interchangeably. So, all right. So now let's see if this runs. Hey, look at that. It works. So the output is identical. And so even though we've gotten rid of like the modulus operator and the division operator, we replaced it with chunks exact, and that's pretty awesome. So this is the first sort of win that we're getting from our vectorized approach. And then the next one we're going to tackle is SIMD diff. So let's do that next. So one thing I actually wanted to add before we move to the next one is the what happens if chunks exact is going to chunk it up exactly into multiples of calls. And of course, in this case, we know it's always going to be multiples of calls because when we allocated the 1D array, we know the size ahead of time, so we know that this will never have a remainder. But we want to be super duper careful. We could do something like this. This is, again, not necessary, but oops, for pedagogical reasons, I'm going to throw this in there. So let's say we do rows iter, and we drop the enumerate here. If we do, we can do something like this. We can say debug assert that chunks, oops, rows iter remainder. Remember that remainder thing when we were reading the documentations is empty. And let's see. So this should never trip because this assertion should always be true. So this trip wire should never trip. So here, if we do a cargo test, you can see, oh look, it passes, no problem. Yeah, because we know ahead of time that we're dealing with exact multiples of this column width because that's how we allocated the array in the first place. But I just wanted to mention that just in case people are wondering what happens if there's some remainder left on because it does say chunks exact. Well, in this case, that'll never happen. So, but yeah, the debug assert is just a little thing to show that okay, yeah, that's true. The next method we can implement is the let's see, where are we? We just did the SIMD print screen. We can kind of do the same treatment for the diff method. So let's see. Let me. What is this? Let me collapse all these. Okay, there's diff method, and let's see, it's doing I guess scalar diff, each row, each column. Okay, that makes sense. And then so with the SIMD version, we're going to use that zipped iterator thing. And even though we're doing this zipped iterator, we're still going to be using the we're still going to be extracting the row and the column because the diff has to give us vector positions. So let's see how this works. Okay, so we can do SIMD diff with self and other. Same thing, backup position, and then, but this is going to be a different implementation. So we'll do the same boilerplate changes, vec, and then we're going to return, oops, what the heck, changes. All right. So here we're going to be doing that same kind of, actually, let's see, how would we do this? I think we got to do the chunks exact. And so the algorithm will go something like, we get the actually the same kind of thing we did here with the print screen, where we chunked the 1D array into exact slices each of this column width. So we can do the exact same thing. So we can say columns chunk size is that, and then we can do self rows iter, and then that's the, yeah, there we go. So we got we chunked up the self one-dimensional array, and then we chunk up the other one-dimensional array. So now that we have two of these iterators, we can do that similar kind of debug assert thing where the self remainder should be, there should be no remainder, and then same with the other one. Okay, so this is good, and that's just to demonstrate that this is the case. Then now that we have two different iterators, one in self and one in the other, now we need to find the zip rows iterator. So not find, we need to create the zip rows iterator. So we can do self rows iter, then we can do zip other rows iter, rows iter, and then enumerate. So this can give us the zipped rows iter. So one iterator on self and one iterator on the other, and then we're zipping them together. And then we can do for, let's see, actually, Control Shift backslash. Yeah, this is right. In zipped rows iter, that's right. So we have the. So what this is doing is that it's gonna iterate through both of the self one-dimensional array and the other self one-dimensional array, and then at the same time, and then let's say that if it's a, we have to check whether it's the same or not. So we can say if let's see, self row chunk is not the same, that's right, then there's there's a diff. So let's see. So now we gotta find. So now we know that there is the rows are not the same. So you can say that we're kind of very quickly drilling down into where these differences lie. So if like two row chunks are the same, then nothing. It'll just go to the next two row chunks. But if there is a difference in that row chunk, now we can drill down, and then now we need to iterate the columns. So here we need a columns iterator where, let's see, we are doing the row chunk. Yeah, we're basically going through the differences between the two rows. So we have equivalent rows on both the one-dimensional arrays. And then now we're looking for each column, can we find a difference? So now this is the, I guess, the zipped columns iterator, because we have a zipped rows iterator. And so here we can do for, let's see, columns, that's right, and this is correct. This is F, yep, that's exactly right. Perfect. Okay, let's go over the exact benefits that we're getting from this code. So the first benefit is that we're bypassing the math pipeline. So we're not using the division or the modulus operator, even though we are actually working with rows and columns, as you can see here. And so that right away, by using the exact chunks, or chunks exact, we're actually doing pointer arithmetic by just adding the width of each what we're calling columns, this one, to basically, like, we're just using pointer arithmetic by adding the columns amount to the pointer, and just kind of like jumping from one row chunk to another, in order to do this zipped iterator, which allows us to bypass using the division of the modulus operator, which is actually quite slow. And the benchmarks will actually show this. So that's one sort of right away benefit we get from eliminating the CPU intensive division and modulus operators. The second one is that this, if you look at this line, we're actually not comparing item by item the contents of these slices. We're just like in seemingly one go, we're just saying, is this chunk equal to that other chunk? And the way this magic works is that the LLVM actually auto vectorizes this code, and it ends up using SIMD instructions. But before those SIMD instructions, we talk about that. It actually uses makes really effective use of the L1 cache or L2, L3 caches by prefetching both of these chunks simultaneously. So even though the self row chunk and the other row chunk, like the full one-dimensional array, which constitutes many such chunks, they're actually in, let's say, two completely different places in physical RAM. Despite that, because the CPU, we know that the data in those two separate locations in memory are exactly the same size, and they're contiguous, what the CPU can do then is actually prefetch both of those disparate physical locations in memory at the same time, and basically pre-populate the L1 cache with bytes from those two different disparate physical locations. So um, the let's see, I think there's let me see how many it can pull. Probably let me see how many it can pull. I think yeah, so we have like multi-stream hardware prefetching. So it's not limited to tracking just one stream of memory. They can track multiple independent sequential memory streams simultaneously, often 16 to 32 streams at a time. So because SIMD diff iterates linearly through self data and other data, the prefetcher recognizes that these are two distinct linear access patterns. They're of the same size. And it fires off a request to RAM for both streams concurrently, which is amazing. So it pulls like the next 64-byte cache lines for both self and other, for both 64 bytes for both into the L1 cache ahead of time. So, and then another benefit is that the CPU doesn't have to wait to read the data for self for it to be able to read the data for other. It can actually fetch the data from two completely different memory addresses into the L1 cache at exactly in the same exact clock cycle. So not only is it reading two disparate locations of memory, it's also prefetching the bytes from those locations into the L1 cache on the same clock cycle, which is pretty incredible. And then so that's the sort of getting the bytes into L1 cache. So that's the magic of like multi-stream hardware prefetching, which is pretty awesome. So it's very efficiently and very effectively and very quickly pre-populating the L1 cache from both self.data and other.data in the same clock cycle. So then another advantage is that if you look at that, so that was just like, okay, get the data into L1 cache. So then now, if you look at this line 196, we're not comparing items item by item. We're just like saying, is this chunk equal to that chunk? And the way that works is that this is called superscalar SIMD execution. So the CPU doesn't check element by element. It instead issues two SIMD load instructions to pull 32 bytes from self row chunk, and then 32 bytes from other row chunk into AVX registers. And I think these AVX registers can be between 32 or 64 bytes, and there's some amount of them. So because the CPUs are superscalar, it loads both the registers simultaneously and then executes so it loads the register simultaneously because the data has been prefetched simultaneously into RAM, into L1 cache from RAM. And then once it gets loaded from the L1 cache into these registers, it then executes a single SIMD compare instruction, yielding roughly 32 byte comparison per clock cycle. So, which is pretty intense and pretty amazing. So, so that's the gist of how we're actually. This is so much faster because we're like unlocking we're basically working with the hardware. We have empathy with the hardware, mechanical sympathy if you want to think about it, or electrical sympathy because it's solid state. So that we're really like helping the code work with the CPU in order to get the massive gains in performance. And one last thing because we're using zip and chunks exact, we know that both self and other we're chunking through exactly the same amount, so there's no need for bounce checking. And so that ends up yielding more performance benefits. So there you go. Those are roughly like 4 of the things that are happening under the hood to unlock or unleash the performance of the SIMD instructions and the hardware prefetching. So yeah, and then so that was the first set of use cases, and then next we'll cover the bulk operations where SIMD will also yield tremendous performance boosts. There are two more methods that are left to optimize with SIMD, and that's actually the second rule, which is so far all the methods we've optimized, we cared about the 2D coordinates, the 1D to 2D outer space translation. But there are two other methods where we don't care about it at all, which is clear. I mean, admittedly, we did a very naive implementation of clear here because we knew that under the hood it was a 1D array, and that's exactly what we're going to do now. So we can say pub fn. Actually, let me see. SIMD diff. I don't know that we wrote a test for SIMD diff. Let's see. SIMD diff. We did not, so we can just write a test for it. So I think we have test diff. So we can do, oh wait, I think the SIMD tests are at the very bottom. Yes. So we can do fn test SIMD diff. And here, oops. Let's see what it's doing. It makes a grid of 2 by 2, populates it with 0. Ah, okay. Modifies. Then that's a cell. This is self, and this is other. Actually, why don't we just call this self and other? Oh, we can't. Right. So self array, other array. All right, and then okay, maybe we can just call it array. And okay. So we have self array and other array. Then we mutate other array so that they're differences, and then we do changes. Okay, let's see if it works. It should, because it's exactly the same code. Okay, now we can do that same thing where we're like compare to scalar diff. So scalar changes. These are SIMD changes. See if that works, and that works. Yay! So that was a pretty straightforward test. Okay, so now coming back to what we were doing is clear. So we need to make a SIMD clear right here. SIMD clear. Take a mutable reference to self, and this is you know, like a character to or sorry, a value that we can use to populate the self data with, and check it out. We just do it. Oops. Just a one-liner. Very quick. That's literally it, because you know, under the hood it's just a single array, right? So this is pretty awesome. And so as we know, self.data is an uninterrupted or contiguous block of memory. So when this code gets compiled, LLVM aggressively auto-vectorizes this into SIMD instructions. And this is actually writing data, not reading data. So we're not like prefetching anything. So this is, we're actually leveraging SIMD store instructions here, which is like a massive memset. So instead of writing one character at a time, because, you know, let's say the buffer is like 100, whatever, like, so however big, we're not like writing one chunk of 1 byte at a time. Instead, the CPU writes 32 or 64 bytes off the default value, or not the value that we want it into the L1 cache in a single clock cycle. And then if it's more, if the data self.data is larger than that, so if the array is larger than the SIMD register, so if it's more than, you know, 32 or 64 bytes, then LLVM creates a highly optimized loop and unrolls it to keep the CPU pipeline saturated. And essentially, even if there's stragglers at the end, it ends up generating scalar code to clean up any leftover bytes at the end of the array. So because it's if it isn't cleanly fit in 32 or 64 byte chunks. So that's all that's happening in this seemingly, this fantastically just one-liner, which is pretty amazing. Then if we look at tests, we can do, let's see, this one will be test SIMD clear. And then here we can do, let's see, so does this SIMD clear on grid? Basically replaces a grid of zeros with a grid of ones. Then it makes other, which has, okay, other is just a array of size 1. And it, let's see, checks that they're the same. Okay, perfect. So here we can do something like this. This is self grid, and this is other grid. And then we just make sure that self and other are the same. Pretty awesome. So with that done, we have one more method we got to do, which is, so we did SIMD clear. I think the next one and the last one is scroll up. That's right. So scroll up, if you recall, this one is actually fast in the Vectorization. So this is the only thing that was fast, like super fast compared to like nanoseconds fast. So this one, even though we're going to do a SIMD version of this, this is one of the ones that will be slower because we just don't have the benefit of, in this case, the benefit of Vectorization. So here, when we do scroll up, this is actually going to end up being slower. But let's see, we can do, I mean, it's gonna be that slow, but it will be much slower than the Vectorization. So here we do row size, wait, row size. Let's see, copy within, let's see, what we're doing here is, let's see, I think it's, well, do self data copy within. So copies elements from one part of the slice to another sort of part of the slice using memmove. So the source range, so let's do let source range is actually self calls as usize dot dot. So that's self range. Actually, source range. What am I saying? Source range. Destination. What's the destination again? Copy within is destination of the usize. Let me see. Copies elements from one part of the slice to another part of a self using memmove. Self is source is a range within self to copy from. Destination is a starting index of the range within self to copy to, which will have the same length as source. The two ranges may overlap. I think we're like overlapping the last self to copy to, so that's a destination index, starting index of the range within self to copy to. Okay, so source range, starting index. So the source range is, so we skip like one column, I mean one row, and then we skip one row. I think we need an ASCII diagram here to describe this. Let me see, scroll up. Why is there an ASCII diagram? Let me see, where's the, I thought I had a diagram for this. Give me just 1 second, scroll up. They're both missing ASCII diagrams. What? Yep, it looks like they're, okay, let me go find the ASCII diagram real quick. Okay, I actually found the missing diagram. I don't know what happened to this, but here we go. This is the what we had before with the vec of x, where we shift the pointers up and then duplicate the last line where we have clone. Then for the SIMD version, I think this diagram describes what exactly is going on here. Oops, what the heck? So here we have, yes, we need memmove. What is this? Okay, so here, this diagram actually, so we basically shift everything to the left, and then since after it's shifted, it just leaves the, like it takes this slice and then it copies it starting here, so we end up with 2 row 3s. So there you go. This diagram explains what exactly this code is doing, just to a T. Perfect. So there you go. This is actually the copy within method, which is essentially similar to um, uh, it's an optimized SIMD memmove call, which shifts a huge contiguous block of memory in bulk rather than moving elements one by one. So, however, even though it's optimized and it's using SIMD for reading and writing, in this is the one case where the vec of x is actually way faster, and we will see that in the benchmark. So even though um, we are copying physically, like bytes that are physically contiguous, even if they're sped up with SIMD registers and prefetching and all that, and optimized writing, it's still not gonna beat the not actually having to move the memory at all, which is what the vec swapping the pointers in that one vec, because that's shifting a bunch of pointers just in a contiguous chunk of memory. So yeah, that's the one case where vec of x is actually faster. So with that done, actually, I don't think we did the SIMD scroll up test. Let me double check. Pretty sure we didn't. No. So let's do this. We can do fn test SIMD scroll, and then that should be, so we do SIMD scroll up. So what we should do is just have 2 of these, right? Because we do let self array equals, oops. And then we can do, what is this? Array, and then we can do self other array equals, then we can do assert equals self array. Okay. And then now we just need to fill this out. Other array. What the heck? Come on, autofill it. What is wrong with this thing? That's weird. I don't know what to say. What is this? What the heck? Um, what? I'm not sure that I meant to do that. Wow. What the? All right, that was a mistake. Let us undo that. Where are we? Okay, that didn't work. Let's do this. Let other array. Now that works. Okay, I don't know what's. All right, and so, oops, this one is going to be that. Okay, so here we have, well, really, this is, actually, it's not really self and other. This is like array 1, and that's array 2. And I think both, let's see, we can probably move this out here. And we can call this the OG array. So we have an OG array. And here we do OG array clone. And then in the next one, we also do OG array clone. And these are mutable. This does not need to be mutable. So basically, we're making the same array, cloning it twice. And I don't know if we even need to clone it twice. I wasn't sure if we're even modifying it. Yes, we are, because we are scrolling. What is the problem here? What? Mute? What is this operating on then? Where the heck is it getting array? Oh, okay, there we go. So fill the array with distinct values for testing. We did that already. You know what? Let's just, wow, my bad. So let's do this. Should have refactored this out before I copied the code. Here we go. This is what I meant to do. And here we say, oops, we're gonna scroll. Okay, this is what I had intended. Okay. So we make the OG array. I don't know why this rendering isn't working properly. Okay. So we make an OG array, fill it with a bunch of stuff, and then let's see, and then we clone it, do the scroll, then we clone it again, do the scroll, but one is using SIMD, so this is, and this is Scalar scroll. Yeah, so we have a SIMD scroll and a Scalar scroll, and they should be the same. So yeah, okay, took longer to write the test than to actually execute the logic of the test. Okay, so there we go. So that in a nutshell is the entirety of actually creating the scalar version of the 2D array that's backed by a slice in memory and a one-dimensional array, essentially, or with we have ergonomic API access. I mean, with index and index mute, so we can use the angle brackets. We have SIMD versions and scalar versions of the same of the operations that we need this particular struct to expose. So this is a pretty fleshed out struct, and at this point, all that's left to do is the benchmarks to validate all essentially the assertions that we've made so far about SIMD being faster than the scalar variants, with the exception of scroll up, where we predict that the vec of x is going to be way faster. So that's next. Now it is time to write the benchmarks. So this, given that we've gone through writing the code, walking through the theory of why it should work, So let's do this. I have to, I'm just gonna copy this because this is, oops, this needs to be at the very top. So for benchmarks, I'm using cargo bench, which is we're not on the stable release channel. Let's see. Pretty sure we switched it to pretty sure we switched it to nightly. Okay, yeah, that's right. I don't know what the hell I'm complaining about. This is just, let's do this. Let's make a benches file. Okay, there we go. And then if we do cargo test, what? Not for sure we did rust up overnight override set nightly. I don't know why this is not working. Cargo check. I guess I could specify. That's weird. Cargo build. This should work. Let's see what's in benches. Anything? Nope. Cargo bench. I don't know what that red thing is. It seems like it, the heck. Wow. Let's wait till this finishes. Oops. What the? I don't know why this is taking so long. I think it's doing a release build. That's why. Let's see what happened here. Warn unused features. What? So do we do allow unused features? Still, this attribute does not have a. It's, but we're not in the stable release channel. I'm confused. What the heck just happened? Oh, what? Let's see. So this cargo test says feature test is declared but not used. Okay. Pretty sure we need this. You know what? I'm just gonna ignore this for now because it doesn't. Let's just close that. Deal with this later. I don't know that that's a. Maybe it's because there's nothing in benches. Probably. Okay, let's try this. Extern create test. Maybe this will make it go away. Ah, wait, that make it go away? Yes, that made it go away. That was weird. I don't know what the hell had happened there. So now it's saying, okay, it's declared but not used. But then if I say, but the, notice the red is gone. So I don't know. Let's see if I do reload window. Maybe I shouldn't have used VS Code insiders for for this video, it seems. Not sure what the heck is going on. Now there's no red, so okay. No clue what happened. Anyway, we will need this. Let us proceed. So here we're going to actually we need some imports. So let me go do some of these imports. So we need use test black box bencher. These are all for cargo test. Sorry, cargo bench. Then we need from our crate. We need flag2d array. We need vec2d array. That's right. And we also need pixel char because this is the type that I'm going to be using in the benchmarks rather than a usize, because usize will, or some scalar type, it will actually make it's really fast, like it's blazingly fast for usize. It's too fast because I don't really use this for usize. I use it for pixel chart, so it'll make the benchmarks look really, really good, but I don't know if that's truthful, at least for the code that we have here. What is this? 2D array. Okay, sure. Make that spelling go away. Okay, so now that we have our imports, we can collapse that. We need a like a size for our testing. So we're going to use const width of row. Wait, width is column width of like 200, and this we will need column width and row height. Perfect. And column width. Oops. My bad. Width. Okay. And we cannot call this. That's fine. We will do column width from 200. Will this work? Oh, maybe that's why we... Wait, what? Cannot call non-const. No? Um, hmm. Really? Okay. Apparently the constructor is not const. Well, what do you know? Okay. Then let's just do usize for now. And then we can do 200 and const, right? It's to 200 by 100, something like that. Okay. Let's see. So, let's see. When we run benchmarks, we're going to see the essentially the times and the variances for these functions, and one of the things we'll see is even though regardless of what the times are, we're going to see that the variance for the 1D array stuff is actually better. So it's a much more stable performance. The P99s or whatever are predictable. So, okay, so let's make our first benchmark. So the way we do this is we do bench, and then I'm just gonna, so that it prints out cleanly, I'm just gonna arbitrarily prefix it with something. So I'm gonna say group1. Otherwise, when the output happens, it's not gonna be easy to read, but this will be. Screen legacy, and this is just a boilerplate for cargo bench, and then we can say let mute grid. We say vec2d array of pixel char. Oops, is what is this? Width plus height, and then variable does not need to be mutable. I'm going to put a bunch of these allow so that we can actually see what are typing. So unused variables and unused mute. All right, so we have vec2d array of pixel char. We're making a new width and a new height. Okay, why don't we just do this? Fn size, this returns size, which is just going to be width and height. That way we can make this code just simple. There we go. That's, I think, much cleaner. All right, so we have we've made a grid. We've sized it the same as the others. And we've populated with a bunch of default pixel chars, and then we're gonna do and this is gonna like run this thing like whatever we say. Grid clear black box of pixel char void. Okay, cool. So this is gonna call the scalar clear, and instead of passing it a type T, it's passing it a black box. Exactly. So it's some compiler hint. All right, cool. Okay. Now let's do this. Cargo bench. And we should get our first benchmarks. It said, there we go. So I wonder why it's running all the tests as well. Just benches, all targets, examples, tests, benches. I wonder. Nope, still puts a test in there. Lib, bin, bins, bin, example, examples, test, benches, bench. Okay, whatever. We can just ignore the where it says ignored. I'm sure it has something to do with one of these, maybe. Not sure. Okay, let's do cargo bench again. So these are ignored. That's fine. There you saw it took a little bit of time to produce the results because it was like running it quite a few times. So here we go. We have how long it took, about 15,000 nanoseconds per iteration. And the variance is 6,000. So that's a lot of variance. And that's kind of what I was talking about, is that the downside of the vec-of-vec approach is that even though regardless of the speed, the variance is going to be quite high when compared to our 1D, the flat 2D array, or the whatever the flat 2D array struct is going to have much better variance numbers, and that's important if you're building a 2E application where you don't want stutters, or you don't want those like once in a while. Like most of the time it'll go some speed, but sometimes it'll be twice as slow, or twice as something. So the variance, this is a pretty big number for the variance, and it's so if you do like 6,000, what is it, 6,000 oops, let's do this. How do I calculator? Where's the freaking calculator? Anyway, 6,000 into 16,000 is like 6, whatever, 33% variance, something like that. That's a lot of variance. So let's do this. Actually, is there like a K-calc or something? Wow. So what is this? Let me do the, where to go? So if I do 6,000 divided by, where's divided? By 15,000? What? 40%. So 40% variance. That's a lot. Yeah, 40% variance. So this is not so great. Then it's like plus minus 40%. So let's see. And that's because of the scattered heap allocations. So this is a consequence of like, having a pointer, like an array which has pointers, and each one of those pointers is pointing to a vec in memory in different locations in physical memory. So this is unavoidable when we use the vec of x. So there's something else to consider. If you don't want these stutters and you don't want like variance is swinging, to like, 50, 40, 50, 90%, then that's another reason to use the flat 2D array or the vectorized version of this, like representing it as a one-dimensional array, as taking the two-dimensional data structure and then flattening it into a 1D array. It has that benefit as well. So now let's do, that was the legacy, not like legacy, let's call it scalar. And then let's do function group one. You're going to do clear scopes, clear screen SIMD. This obviously got it wrong because it was SIMD. I think it's SIMD clear. Yeah. So maybe we can do a screen scalar. Yeah. So then we can see the, yeah. So, okay. So when we run cargo bench now, you'll see what I'm talking about. So what? I forgot hash bench. One more time. So it's not running, it's taking a while because it's doing the benchmarking, like it iterates through some number of times. So let's see. Look at this. The clear screen scalar is 16,548 plus minus 8,000, 17,000 plus minus 14. Wait, how do you read the variance? Interesting. Maybe I read it wrong. Let me double check this real quick. Okay, let's see how big the grid is actually. Because I think the reason, I think the cargo bench is, oh, this is cargo bench. I think these numbers are correct. So I think what this is saying is that for the scalar one, on average, it's taking 13,000 nanoseconds, which is 13 microseconds, and then but the plus or minus was like you can take 13 plus 9, that's the max, 13 minus 9 is the min. For the SIMD, it's actually slower. It's 20 plus 13, which is way higher than 13 plus 9, and 20 minus 13 is it's 7, which is 13 minus 9. No, so it's still higher no matter what than the scalar one. So SIMD here is slower, and I think I think the reason for that, well, even though it's slower, they're very similar. It's not like one is that much slower or faster than the other. So let's do this. How big is the exact grid size? I want to know this, and then we can put it here as well. So this is going to be the, let's see, for Vec 2D array, that's the grid size, and for flat, because I'm wondering if we're spilling over, because on this CPU I just checked, For the E cores, it's 32 kilobytes is L1 cache, and for the P cores, it's 48 kilobytes. So let's see how big this size is. So let's see. Let's do cargo bench, no capture group 1, yeah. And then this will give us, okay, so, so the grade size is 642K. So about 640K, which is way bigger. So here we can say Intel CPU, we have the P core is 48K L1 cache, and the E core is 32K L1 cache. So if that's the case, and we run this again, so what are we getting? 13. Oh, by the way, the reason we wrapped this thing in a black box is so that LLVM couldn't optimize it away, I think, because that would kind of like not make the benchmark that useful. So let's do this again. So we have 16 plus or minus 9, 19 microseconds plus or minus 13. So that's not really changing. So the vec is actually better in this case for clearing than the SIMD. Because I think it doesn't matter. We're spilling out into the L1 cache, and now we're just like accessing memory. So if I'm just gonna do this real quick. Let's see, let's do this. I'm gonna make this what I think, I don't know, what, 30 by 30 I think will fit into this. So oops, what the heck am I doing? Let's run this again. Okay, so the numbers are way smaller. So here we can see for the Vec2D, I wonder what it would be for the non-SIMD clear. Curious. It's about 29, 30K. So these numbers are pretty similar. The Vec of X and the, okay, what if I do, okay, so this is clear screen for Vec, Vec 2D array. And here we do Vec, oops, flat 1D array. Actually, let's do the, this one we can call it Scalar. So here we can do, okay, let's see what results we get here. This should be interesting. Okay, so what? So the Vec2D scalar is slower for a grid size of about 30K. The vector, wait, what? The Vec2D array. Okay, so let's do this. So I want to present the numbers of this first. Maybe I'll do 1 and then 2, just for sorting. Yeah, let's do that. Nope, Vec2D array still run first. Why? Group 1. What? Group 1 clear screen. Okay, let me just drop this. This didn't help at all. Okay. So here we have, all right, so the Vec2D array is 389 plus or minus 218. Flat 2D array using SIMD is 205. So that looks like this is the winner. And then when we do scalar, that's 346. What? Okay. So it sounds like in this case, with the grid small enough, our intuition is correct. This is essentially in between the three. This is slowest, but that's with the within the like a small, like this is not a realistic. I mean, this confirms our hypothesis that when it fits inside of the cache, this is what happens. Maybe we should do two variants of this. Like maybe we can do maybe it should be something like, maybe we can do something like this. We can say mod bits in L1 cache. Then this would be like, oh crap, we can't have a size anymore. So maybe we should do so here what, okay, so this is to make it fit in an L1 cache is what we're doing. So we can say something like this. So this is group 1 clear screen. I mean, this is fits in fits, right? And this is fits and this is fits. So if we do like this, because we should do another one where it doesn't fit. So we can say fits in L1 cache size, something like that. And this one we can do like this. And then this one can be size. Man, these benchmarks are never what you think. All right, so let's run this again. So now we're going to see, let's see, the grid size of whatever, 20, 30K. So we have test benches, fits in L1, actually, in L1, in L1. I make the names a little bit smaller. Fits in L1, this is group. Okay, let's run this one time. Group 1, oops, there's no group anymore, so we can just do fits. Okay. All right, so let's hide this so we can get a little bit more width. So we're seeing, so fits in L1, we're actually, you know what, instead of group 1, I'm just going to do G1. Okay. So let's see. So the grid size is about 30K, and we have, okay, fits in group 1. So fits in L1 group 1. And then let's see, fits in L1. Maybe we can just call it, actually that's fine, fits in L1 group 1. And so we got clear screen flat 1D array scalar. Okay, let's start with the vec first. So the vec 2D array, we got 400 nanoseconds plus or minus 72, which is pretty good. Expectedly, the SIMD one is the fastest, and the scalar is not as fast, but it is still faster than the vec. Okay, so that, I mean, that affirms this this confirms the SIMD is faster in the situation where it's fitting in the L1 cache though. So what if we make another one with spills, right? Spills L1 cache, it does not fits. Actually, why don't we just do fits L1 cache, not in? Okay, so spills F1 cache, this, sorry, L1 cache, this is gonna be like 200 by, I don't know, 100, something like that. So that's a much bigger data structure. So here, if we do the same thing of clear screen, I think we're going to see the same, obviously, the same thing we saw before. So here, if we do fn spills, okay, so spills, and this is vec2d scalar. And then we can do another one of this, which is fn spills. No, we'll do SIMD. I mean, I could do the similar one. So sure, why not? Let's do scalar. And then what is this? Then we can do one more SIMD. All right, so now we're doing the same thing, but this is, well, should we call it group one? Sure. So I'm gonna do spills group one. That's the, this is the test time, I mean the benches I'm gonna run. So we're gonna do spills. So we're gonna do like a realistic, like a 640K buffer. And then, okay, let's see what the numbers are. So we got, actually, what is this? Why is this so big? How about spill? Fits and spills, no? Is that, no, it doesn't help. Okay, let's do this. Roll back that change. Let's just keep it spills. I'll just make the window wider. I don't think we need such a huge, all right. Okay, so let's see what we get here. All right, vec2d, oops, it's still, that's going on. Okay, there we go. So vec2d scalar is 16 microseconds plus or minus 7. SIMD is 13 plus or minus 8, so it's lower. And then flat 1D array scalar is 22. This is the worst, actually. This is worse than the vec. So whatever it is, don't use the scalar fill. That's the absolute slowest. So this is, and this is hitting the memory wall, like spilled out of the L1 cache, and now we're just in traffic jams, waiting in line for memory. Well, not traffic jams, more like the CPU is idling, and that's why the time has gone up. And this seems to be the worst. Clear screen scalar. This one. Yeah. Okay. Huh. Interesting. I guess we're iterating it, that's why. One at a time. Okay, that makes sense why this would be slower and this is faster. Okay. I mean, it isn't as clear as before because whether it's within L1 cache, whether it spills out of L1 cache, that starts to matter. But this is the it is what it is, you know. I mean, the hypothesis is correct. It's just that we also have to take into account fitting in L1 cache versus spilling out of L1 cache. But actually, so with the real world results, let's say with the 640K buffer, with the vec, we're seeing 14 microseconds plus or minus 9. So here you could see we ran it a couple of times, and these numbers are not exactly, they're not always the same because it depends on what's going on in this computer and how it's managing memory allocation at the time. So it's pretty close, 14 microseconds, 16 microseconds, you know. whatever it is, don't use this one. That's what I'm getting from this, is if you, whatever it is, don't have a flat 1D array and use a scalar like item by item clear. That is absolutely the worst. Consistently, I think it's worse. And what I'm going to say is that in between the SIMD and the Vec we're pretty much neck and neck. Only when it fits in the L1 cache will the SIMD be a little bit faster. But even then, I would say it's pretty equivalent. So yeah, not a clear win for SIMD and not a clear loss for Vec. So Vec is not that bad in this particular case. So wow, with that super complicated group 1 benchmark out of the way, let us, so from now on, I'm just going to leave this fit side. I don't think is, I mean, unless your use case supports this, which fine, it's fine to use. But in our case, since this was meant to model a terminal emulator, who has a 30 by 30 terminal window emulator size, so I think 100 by 200 by 100 is more realistic. So okay, this was group 1. So let me just put some comments in here real quick. So this is group 1, and this is for clearing. Okay, I mean, yeah, it's not bad. It makes sense. So let's do group 2 now. So this is going to be scrolling. I think we already know who's going to win this one, because Vec is going to win this one. So we can do group 2 scroll up benchmark. So let's see. Oh, G1. Ugh. Maybe I should rename these. G1. G1. I don't think I like those other names. Let's see. G1. Ugh. Wow, complicated, but I think it's fun. Understanding memory, hardware, it's all good. All right, let's see. So now I think if we were to do this, it wouldn't be, it would just be G1. Okay. Okay, that works. Cool. I mean, why wouldn't it work? But yeah, okay. Excellent. All right, so now we're going to do group 2. So this one is going to be, let's see, we're going to do, no, we're not going to do fits in. We're going to do spills, scroll up Vec2D array. That's going to win for sure. Well, I don't know. We'll see. I think that's going to win. I mean, I don't know for sure anymore, but scrolls effect flat 1D array, is that SIMD or what? SIMD. So let's do scrolls up. Man, these names are terrible. Scalar. And this one is SIMD. Okay. So spills L1 G2. Yikes. All right. Well, G2. Okay. Holy crap. That Vec wins. Like, that's not even a contest. 100.1 microseconds. Variance of like nothing. 100 nanoseconds, variance of 100 nanoseconds. And for the SIMD flat 1D array, we got 7 microseconds plus or minus 3 microseconds. Whatever. I mean, we knew the Vec2D was gonna just decisively win this one. Like, there is no yeah, that's pretty obvious. So here actually I'm gonna put some analysis. I'm gonna say slowest is the nope, the flat 1D array clear. This is the scalar. Then medium is the Vec, and fastest is, wait, is that right? Let me see. G2. Actually, there's two numbers here because it depends, right? It's like fits versus not fits. So we should do like this: fits in L1 cache versus spills L1 cache. We actually get different results. Okay, so this is spills, I think. Yeah, we got the vec is 17, SIMD is 8. See, these numbers are all over the place. Now the vec is, I mean, the SIMD is the fastest, vec is second, and this one is third. So if we run it again, who knows, maybe we'll say slightly different results. All right, so, okay, so if it spills, the slowest is the, nope, slowest is the flat 1D array with scalar clear. Medium is the vec, and fastest is flat. And if it fits, then it's actually what we expect. The fastest is going to be, actually, I don't know. Let's see if it fits. Which one is the fits? Oh, fits in. What? Is it? These names are so spills. Oh, spills L1. So fits. Let's do this. Fits L1. Fits L1, and this one is also fits L1. All right. So spills and fits. Let us see what the results are going to be for this one. Okay, so the vec is 400. The flat 1D array with SIMD is 177. Hey, it's actually, the ordering has not changed. It's actually still relevant. It's the same. So whether, you know, fitting or not, it's the same. The ordering is the same. So flat, yeah, flat 1D scalar consistently performs the worst. The SIMD is, wait, what? The vec is slower. Whoa, whoa, whoa. Okay, so the slowest is the vec. Wow. So when it's in the L1 cache, the vec is the slowest. What? Yeah, that's right. The vec is the slowest because that's the whole point. Like the SIMD is giving you the superpowers by, let me see. Yeah, vec is the slowest. SIMD flat 1D array is the fastest, and the scalar is somewhere in the middle. All right. Okay. So this one, wait, what? Flat 1D scalar is in the middle. Okay, so, okay. Makes sense. Makes sense. Wonder if I should put it like this: slowest versus fastest. So fastest, medium, slowest, like that. 1, 2, 3. And this was like 1, 2, 3. Okay. So if it fits, the winner is, if it fits, the winner is obviously SIMD, and if it doesn't fit, the winner is still SIMD, but the thing that changes, the vec goes from second place to, sorry, from third place to second place if it spills. So, okay, cool. This one we don't need to really, this is spills. See, what's our format with a little space, I think. So if it spills, then we can do, let's copy this. Nope, this one we're not even doing the scalar for the flat 1D array. We're just doing scroll up. So we're seeing, oops. So the winner is actually this, hands down, like by a huge margin, actually. The Vec wins. Okay, so now we have group 3, which is, what is this? What benchmark should we measure for group 3? I think print screen maybe. Let me see, traversal chunks. Let me look at this real quick. Okay, let's do group 3. So group 3 benchmarks are going to be like you're reading the data structure. So essentially reading the contents of it from beginning to end. So we're going to say these are going to be reading benchmarks. So essentially print screen, if you want to think of it this way, like print screen benchmarks, but we're not going to be using the print screen function. Why? Because the print screen function allocates a string, which is heavy, and we want to like focus on the code, the iteration parts rather than string allocation. So we're going to take that out. And so this is going to be like what happens inside of the print screen function, if you want to think of it that way. So this is going to be bench spills L1, oops, L1, group 3, print screen. This is going to be vec2d array, scalar. Yep, that's right. That's right. And then I think we're going to do, let's say, size, whatever. Oh, spills, grid is whatever, pixel char. And, you know, we don't need the grid size anymore. We know what the grid size is now. So here we can do, actually, never mind, keep the grid size. Why not? So here we can do p.iter. We're not going to do print screen, but we're going to do what print screen does under the hood, which is we're going to do for row in grid dot rows as usize. What? Oh. Just needed to make it pub. Okay. So, okay, let's see. So we made a grid. We're going to print the size of the grid. Then we're going to iterate that row by, row by row, column by column. And we're just going to like just access this. And then for this one, we can do a similar one. We're going to do spills, flat 2D. Oh, no, not scalar. This is going to be SIMD. And this is not, no, we're not going to do this for loop. We're going to do, and not, no, we're going to do for item in, let's see, actually so it doesn't optimize this away. We need to wrap this in black box. And so it doesn't optimize that away. We need to wrap this in black box. There we go. So now we have item by, we're accessing each item at a time in the vec of x, and we're accessing each item at a time with this. And our prediction is that the flat 1D array SIMD is going to be faster than the vec Vec2D, and without further ado, let us verify this. Hmm? Oh, oops, spills, my bad. Just clear the screen. Okay. What's going on? Spills? Oh my goodness, spills. Okay, here we go. Let's see. Okay, the Vec did 14,000 nanoseconds, like 14 microseconds, plus or minus 5 microseconds. And unexpectedly, the SIMD absolutely trounced it. Like, look at the difference. 14 microseconds versus 3 microseconds. Look at the variance. Not even microseconds, like 996 nanoseconds. So this is clearly the winner, like not even close, which is pretty much why we are doing this, right? Like this was our hypothesis that this would be the clear winner, and it is. By a margin, like not by a small, like so yeah, win some, like I said, it's not clear. The in this benchmark, the Vec trounced the flat 1D array, and in this one, the 1D array is trouncing the other one. So what are you gonna do? Okay. Nope, not scroll. This is gonna be print screen. Oops. Let's do this. Come on. Okay. So yay. That is exactly as we had expected. Now we're gonna do group 4. What is group 4? Actually diffing, I think. Yeah, diff. So group 4 is gonna be diff benchmarks. And let's see. So we're gonna do spills, yeah, Vec2D scalar, that's right. So we're gonna do, let's see, honestly, I don't know what it's doing here, but that is not correct. So we're gonna make a grid. Oops, the heck. So we made a grid. We're gonna make another grid. 2. And then for grid 2, we're going to make some changes. We're going to say grid 2 what is this? So we're going to change 50, 50, 50. What the heck? Actually, just make it void. I don't really care. So, void, because I think default is not void. Default is, oh, default is void. Wonderful. Let's make it spacer. Okay, so we changed one of the ones to whatever, the 50th, 50 by 50 to spacer. Now if we do this, let underscore equals black box. We do grid 1 diff grid 2. Oh, this needs to be renamed grid 1. So yeah, we're basically saying like go find the diff for this thing over and over and over again, and unsaturated, yeah. So we predict Vec is going to be slower because, just like we showed with the iteration, the L1 cache and the prefetching just kind of like this wins because it doesn't have a jump around like because of the Vec of X. Okay, so let's see, bench fn flat 1D array bencher, yes. Let's see. So grade 1, grade 2, what's it doing? Multiplied by what? Why? What? Hmm. I don't know what it's doing. You can just do 50 by 50. Like, I don't know why it's doing. We have index mute implementation for both, so honestly, I have no idea why it's doing a positional one there. I don't. What? No? Oh, thought we did index mute for usize. Hmm. We did index mute for usize. What's going on? Grid 2. So if I do grid 250, right? How does grid 2? Oh, because. Why? Like that. I don't know why I put dot data. That was my bad. That's why. Okay. Because this is the Vec of X, and we didn't implement the index mute for the Vec of 2D array, but we did for this one. So, oops. All right, and now finally we can run this. So spills L1 G4. Let's see. So wow, the SIMD was what, 16, and the other one is 19. Oh, so it's not like that big of a difference here. Interesting. I mean, obviously the SIMD is faster, but it's not like twice as fast. It's like, 1 point something. It is faster. It is faster. Okay, it is faster. All right, so unexpectedly, it's faster. So here, the winner is this one. By like, what is it, 14? Let's do the calculator. So I think it's, what is it, 14? What was it? 16 versus 18, 14 versus 17. So 14 versus 17, it's like 20%. Yeah, 20% faster, I think. So 18 versus 16. So we can do 18 divided by 16. Oops. 12% faster. Whatever. Between 12 and 20%. Still, not bad. Not bad. Okay, so as we suspect, this one is faster, but it's not like 100 times faster. It's like 20% faster, let's say. It's still faster, but it's not like mind-blowingly faster. Let's see. Okay, diff screen. Let's see. Did I do this correctly? 50-50. So we just basically change one of them. And then I think Excel chart default was void is default. So spacer You know, why don't I just do this? I don't know what the heck. Instead of freaking looking it up, you can just do this. Void. You know, set it to void. So let's run it again. It should not make any difference because default was void. So yeah, 16 versus 18. So let's see, kcal. So 16 versus 18 minus 1. So whatever, 11% faster. I mean, still not bad. Variance is better actually. Look at the variance on SIMD. It's really good. So actually the variance is the bigger winner here. So mm, this one like feels much tighter variance in the diffing. So that's pretty cool. Yeah, see, like only like plus minus 5, whereas this was like plus minus 13. So you can see the differences there. Okay, then I think we got, what is it, group 5? I think group 5, what is this, memory? Memory size, yeah. So we can do fn, oops, benches, bench, fn, spills, memory size. Okay, and then we can do the similar thing for fn, yep, oops, bencher. All right, and box, yep, get memory size. So let's see, group 5. Yeah, unsurprisingly, this is always going to win because here we're traversing vec of vec, you know, vec of many vecs, and so that's taking time. Whereas this one is just a flat 1D array, which takes like literally no time. So this is not even close. That yeah, I mean, again, we're not surprised by these results, right? So, and finally we have traversal. I think this is traversal would be similar to what we did for print screen, where is the print screen? I think a print screen, what do we do? Oh, we just did it iter. Okay, so this one's gonna be, okay, I see. We're gonna do one more where this is gonna be we're gonna call it traversal by row and column. Which is very similar to group 3. In fairness, but slightly different because here we're actually going to be using the rows and columns. So which one is this one? Scalar, yes. So we're doing row, you know, we're going to, for each row, go through each column. So row 1, all the columns, row 2, all the columns, and so on and so forth. So this is 1 by 1. But instead, what we should do is let's see. Actually, that's right. So here we can do spills. Um, hmm. Maybe we should show the, you know what we should do here? Should only be, well, so this is for vector, yeah, that makes sense. And then for here, we should do spills by row column SIMD, and let's see. We should also do another variant of this. Row column SIMD. So this is row column flat. Da, 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 da. This is using modulus. Modulus and division. So this is kind of made up in the sense, oops. So here what we're doing is that we're going to do for index item in grid. Yeah, so we're just, remember we talked about modulus and the modulus operator and the division operator, how they were slower. So we're gonna, for the SIMD one, we're gonna show like, okay, for this one, there's no modulus operator, just like rows and columns, because the thing is structured as a 2D array. This is a 1D array, which we're getting the rows and columns using the modulus and division operator, right? So that makes sense. And then let's see, row column item, column item. So basically here we are, wait, did I get this right? Yeah, grid data row. This is so that it doesn't throw it away. This is like, don't optimize this. Like do the calculations and for row, column, and item. Just don't throw the results away. Here we will do the, let's see, what is this? Let's see, this is not right. So we're gonna do let's do this grid data. We're gonna, that chunks exact thing, we're gonna do that chunks exact thing. So, oops. Hey, this works. Yeah, chunks exact, get the whatever, grid columns, and then enumerate them, and for each, given the row and the chunk, get the row column. That's perfect. This totally did it. We just like kind of started with the iterators, just slightly different syntax, but yeah. This, I think this, let's see, read black box. Yeah, okay, cool. So we got the row column item, and we got the, well, let's see. Well, why not? We do row column, whatever. Something like that. Okay. That's the item. So that they're all consistent, right? So let's run this. Let's say group 6. All right, drum roll. This is the final benchmark, and then we get to wrap the video after this. Okay, let's see what numbers we got. Oh, quite wide. What the heck? What? Okay, so we got Vec 2D scalar. We're doing 17 microseconds. Wow, SIMD mod and div, that's a clear loser. And holy crap, that's fast. All right, flat 1D array. So this is why we're doing these benchmarks right here. I mean, this is why we made the flat data structure, and this shows the winner, which is a SIMD. And look at the variance. I bet the variance is, yeah, the variance winner in this case is the SIMD. So unsurprising, it wins. This benchmark is going to be reported a little bit differently because we're actually comparing the SIMD against itself. So it's going to be a little bit different, but so we're going to do spills. So actually, well, no, not print screen. This one is actually, it is kind of print screen in a sense that we're accessing each item. So this one, we actually have print screen SIMD and we have scalar. So I think the SIMD scalar was a loser. So this one is like the don't do it. This is awful. And yeah, so there you go. Perfect. All right. So yeah, on that note, that pretty much confirms, uh, this validates everything we're talking about. Performance you should measure, depends on whether there's so many variables. It's difficult to have an intuition to make an assertion one way or another. We saw that, it's not there's no one size fits all. And just because the flat 1D data structure is faster in some areas, it's slow in other areas. It has better variance in some areas. So yeah, it depends. And for TUIs, this is a clear winner. Like scrolling for full screen TUI applications in alternate mode, this is a no contest. Like this, depending given the use case, this is a clear winner over Vectorization. But if you have a situation where you really need to shuffle around a lot of lines, very very quickly, then this the Vectorization is not bad. So yeah, and let's see. I actually published the tutorial for this, so you can check out the tutorial on developer life. And also I have Osmo address. Oops, so the heck is this? Rust Scratch, and I'll put this in the description of the videos, so you can have this. What is this? Flat. There it is. So all the code and everything is in here. You can check it out if you want to play with it. And yeah, I'll clean up this thing, but I was kind of mucking with it as I was recording this video. But yeah, I will share a link to this in the description of the video. And of course, I will share a link to this as well. This is actually the docs. This is the Rust docs for the actual production code. That's in Rebel Open Core here. So, all right, on that note, thank you for watching. I know this has been a really long video. If you like the style of this video, please give it a thumbs up and subscribe. And yeah, I will do more videos like this when I get inspired. Thanks again and have a great day.